Hello. 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 Where is
Alexei?
Good to see you. Oh, Felix, you are there, huh?
Yes, yes.
So we are running late. I suppose we will have at least 30 minutes for the panel because we need time and we're running out of time and still preparing the paperwork for the panel. I am very sorry. Okay, so regarding the awards, Felix, excuse me, but I hope you accept my solution of the awards. Because let me explain, okay? Awards for
recording
talks,
in progress.
Awards for talks worth nothing, and awards for talks are a nonsense in general in the scientific world. Nobody gives an award for a talk. Awards for papers are of very little value for researchers. What is valuable is an award for an outstanding research over considerable time, right? And yeah, so please accept my solution of that I said.
Okay, no problem.
Thank you.
No
Thank
problem.
you very much. Okay.
In 2 minutes? Okay, you can ask if they can hear, if they to test the system.
Pero voy a estar allá.
Sí, aquí, tú vas a estar aquí. Yes, I know.
Can you hear me?
So we shall give a talk with Anna Zinina.
Activo la cámara. A ver, no sé cómo usar esto.
Ahí está. Abajo. La cámara la conectamos a esa. Ok. Okay, perfect.
Hello, can you hear me?
Tienes el teléfono.
Yes.
El micrófono.
El micro, vale.
Yo creo que ahorita sí para acá, porque no creo que haya mucha audiencia.
Hello, can you hear me? Is the audio okay?
Hello.
No?
No, dijeron hello.
Hello, is the audio okay? Can you hear me?
I can hear you.
Okay.
Okay, perfect. Welcome everyone. I am Luis Parra. I will be the chairman in this session. We will start with the talk with learning a foreign language vocabulary with a companion robot. With Anna Zinina and Artemi Koto. You have 15 minutes to present and 5 minutes for question from the people, from the public. So, are you ready to start?
Okay. Yes.
Yes, perfect. So, welcome. Let's start.
Okay. Hello, everyone. My name is Zinina Anna, and today my colleague Artemi Kotov and I will present our research. I would like to start by saying a few words about our laboratory at the Kurchatov Institute. We are developing an anthropomorphic robot F2 for human-machine interaction experiments. The kinematic scheme of the robot allows reproducing human emotional movement. A robot has moving hands and a head with a monitor for face projection. It is designed as a simple and reproducible research and educational platform. Now let's go to the topic of our presentation. Today, social robots find application in various situations. We find it interesting that social robots are widely used in education, in particular in learning a foreign language. Even more, today we can say that there is a new and rapidly developing field in science, robot-assisted language learned, or RAL. And it is already known, you can see it on the picture from this article. that RAL has shown positive effects on language learning. And also it should be noted that this area is represented predominantly by foreign research. Russian researchers have not conducted such experiments. So we decided to do it, and we conducted an experiment in which the robot acted as an assistant in learning the vocabulary of foreign language. We assume that personal interaction between a human and a robot could facilitate the students' engagement and the satisfaction with the learning processes compared to the more traditional needs, a computer program with a screen interface. The experiment was conducted in spring 2022 at the Moscow State Linguistic University. Subjects were students. On average, the experimental procedure was 20 minutes. At the beginning of the experiment, the person sat in front of the robot or the computer. The experimental introduced the procedure of the experiment and left the room. The slide shows a schematic illustration on the experiment with the robot. And you can see two stages, word presentation and the word training. At the beginning of the experiment, the subjects were presented with their studied words. They saw the word and its translation on the monitor and hear its pronunciation in the Latin language. In addition, a hint, a special keyword, was presented to the person by the robot. After that, in the second stage, the subject was presented in the word in Russian by the robot. If the person didn't remember the word, the robot gave them a hint, and if the subjects didn't answer again, the robot started recording the pronunciation of the word by a Latin speaker. All the hints, keyword, and the Latin reading were presented in fixed 5-second intervals. Words were presented twice. Subjects' answers were controlled by experimental, so we used the Wizard of Oz paradigm. After learning, the subjects was invited to the next room, where the experimental checked the words learned in both experimental conditions. We choose oral form of verification because it corresponded to the oral form of responses in the experiment. We use within subject experimental design. It means that each participant was practicing Latin words with the robot and with the computer. And now you can see more detailed presentation of the second stage, word training with the robot. And now I'll show you a brief version of word learning with the robot. There is translation.
Сейчас мы познакомимся с латинскими словами.
Conable.
Как парабола.
Arboris.
Как барбарис. Хорошо. Теперь пробуй назвать латинские слова, а я буду тебе помогать. Дерево. Как барбарис?
Арборис.
Ага. Колыбель. Как парабола.
And in this slide presents the scheme of the second stage of the experiment, but without the robot, with the computer. And now I also present you a brief version of experiment.
Programmable. Arboris.
Arboris.
For the experiment, we used keywords as hints. We chose 26 Latin words with low frequency in Russian. We used phonetic hints suggested by 42 native Russian speakers. Suggested hints were semantically unrelated to the Latin words. So for each Latin word, the most frequent Russian keyword had been chosen and then pronounced by a Latin specialist and recorded. The words were randomly divided into two groups for each of experimental condition. In the table, you can see examples of Latin words, their translation, and keywords. So let's move to the results. And according to the results, subjects were equally successful in learning Latin words in two experimental conditions. As I said, each word was presented twice, and based on the data, we can also observe how words were learned. The number of wrong answers decreases, and the number of right answers increases. And for us, it was very important to evaluate the attractiveness of new methods of word learning compared to a well-known way. And according to the results, about 60% of entire sample indicate that they preferred learning words with the robot. And the differences in preferences are statistically significant. After the experiment, the subjects filled out a questionnaire in which they evaluated their impression of foreign language learning. For this purpose, we used semantic differential scales, and according to these scales, the participants described the robot compared to the computer as rather friendly, cheerful, emotional, responsive, and attractive. And the computer is rather apathetic and quick. We also evaluated user satisfaction from the interaction with the robot. For this purpose, we use the modified satisfaction questionnaire. And according to this questionnaire, there are 4 satisfaction factors. This is efficiency, ease of use, usefulness, and emotional attractiveness. And according to the results, such factor as emotional attractiveness in this graph and usefulness in this graph of the robot correlate with the preference for one or another way of interaction. Analyzing the data, we found that subjects show a rich emotional expression when interacting with the robot. They ask questions, ask for hints, say that they do not nothing, and they do not know correct answers. We also found that the robot received more smiles than computer, and now I will show you 2 examples. In these examples, respondent smiles when answer is incorrect.
Вопрос.
A very rich emotional expression.
И не вспоминается.
Как клавиатура.
And another example.
Как клавиатура.
Славус.
We'll see smiles from respondent when the answer is correct.
Кальциус.
Да.
It is very interesting. These subjects do not show similar behavior when learning words with the computer.
Как мозг.
The subject tends to positively perceive the robot as a learning assistant. Even those subjects who prefer the learning words with the computer, noted that personal interaction with the robot could be effective for learning foreign language. We asked the following question: can personal communication with a robot be effective for learning foreign language? And 57 subjects said yes. And here you can see 3 different groups of subjects depending on the role of the robot in the educational situation. First, we can differentiate those subjects who confidently perceive the robot as a teacher. And secondly, the subjects may focus on the robot's creation of more comfortable environment for learning and supporting a pleasant and friendly atmosphere. And thirdly, there are subjects for whom the support of the robots is significant. They also note increased motivation to learn the language when interacting with the robot. And despite the positive responses, there was a group of subjects that liked this interaction less and preferred the computer. And such subjects were divided into subgroups. First, some subjects noted that the methods of hinting through keywords didn't suit them. And secondly, some subjects found it difficult to concentrate on learning words with a robot. And our conclusions, according to the results, the robot has a good perspective to be used as an assistant in learning a foreign language vocabulary. And the robot gives a positive impression and increases motivation and desire to use this method of learning in the future. Students highly evaluate the flexibility of the robot in this. And thank you for your attention. This is our lab and our website where you can read more about our work and about F2 Robotic. There is Artemio.
Okay, thank you so much for a very interesting presentation. So we can start with the question from the people.
Что-то в чате.
Hi. I was wondering here that it will be possible to have in the computer a face like just you have in the robot, but without the rest of the robot. Do you thought about having this intermediary kind of experimentation where you have not just a computer without anything, but a computer with a face, for example, that could give the same kind of impression that the robot gives, but without the robot apparatus?
It was our first research, and we decided to compare robot and computer. Maybe later we will compare robot and face something with face interface.
I would say that it is important for us that a robot gives an impression of a presence of some entity, some guy in the room. And in fact, you can walk around the room and listen to what the robot says and answer to the robot. But it is difficult to compare that in the experiment, because in the experiment, subjects had to sit in front of the monitor or in front of the robot. But in an actual situation, it is possible just to do what you usually do in the evening, and the robot just is training the words orally with you. But you are connected because you feel the presence of the robot. So this is important, and that's a question how to organize the experiment you are talking about.
Yeah, I'm thinking about having the same presence of an agent, but an embedded agent inside the computer and not in the real world like a robot. It could be interesting to have a comparison between two, let's say, characters, the character in the robot and the character in the computer. And then maybe you can have a better understanding of what is the difference of having a full robot and having a character inside the computer, and maybe this could be an interesting experiment for the future.
Maybe. Thank you.
Okay.
Someone want to ask another question?
Thank you.
No questions?
Thanks a lot.
Okay, so we thank you for your presentation, and we conclude this blog. So thank you very much, and have a nice day. Okay.
Thank you very much. Bye.
No sé cómo usar eso. ¿Qué quiere hacer? You're right. Alexei?
Yes, yes.
We can start the panel.
Oh, I thought you had another talk before the panel, no?
No?
All right, let me just transfer the PowerPoint presentation I am making to another computer. Or what is easier? Is easier to connect? No. Just give me 1 minute, okay?
Okay, no problem.
By the way, Felix.
Yes?
I would appreciate if you prepare the list of awards, because I had no time to list them in PowerPoint.
Okay.
Okay. Thanks.
Okay.
Hello, Felix. Hello, Alexei. Hello to everybody.
Hello. Hello.
Hello, Alexei. Hello to everybody.
Can you hear me?
Yes, yes, of course. Yes,
Great.
of course.
Do you see my screen?
Yes, yes, of course.
All right. So we can start.
David is in the meeting.
David is not present. Who is present of the panelists of the panel?
It's
Not too much.
Not too much, no. It's you and me.
I'm here as well.
Well,
I'm here as well.
Okay, nevertheless, I propose that we start our BICA Society panel now and pretend that all the panelists are here. I see Kirtin.
Yes, can you hear me?
That's probably the main person that we need today. Okay, so, Tin, hi. Hi. Nice to see you. That's great that you could make it.
Zhenliu also comes.
Sorry?
Zhenliu, Professor Zhenliu also coming.
Is he joining?
Yeah.
Okay.
刘老师, sorry, I call him. 刘老师。
Nice to see you.
Nice to see you. Nice to see you. Let me start with my presentation first, and then you give your presentation, okay? So I'm afraid to put it in a presentation mode. I guess it doesn't matter. You see what I have on the screen, correct? So if you see my screen, then I guess I can start.
Yes, we see your screen, Alexei.
You can see it.
All right.
Yeah.
So hello everybody, and this is the BICA Society panel of 2022 in Guadalajara, Mexico, held virtually. Today, I have to tell you first that BICA Society is doing great. It is a non-profit corporation and is also a scientific organization. It is incorporated in the United States, and the purpose is to support and facilitate every effort to solve the BICA challenge. And the BICA challenge is to create a real-time computational equivalence of the human mind, capturing its highest cognitive functionality using solutions inspired by the brain. we have the key activities. First of all, our BICA conference. Then we have a series of publications, of which the main one today is the Journal Cognitive Systems Research. It is a Q1 journal in psychology and in software engineering. Currently, we have a new open issue in psychologically inspired cognitive systems. You all are welcome to submit papers. We also have somewhere a repository of our community online. So here's the brief statistics of the BICA conferences over 14, 15 years. Actually, it started in 2008 as AAAI Symposia. Since 2010, it is a conference, and we see that there is no declining in the number of participants or submissions. Actually, there is a little growth during recent years, and we expect it to grow even more in the coming years. So now is the year of election of BICA Society. It happens once in 3 years. And let me remind that the current directors of BICA Society are David Kelly, who is not present, unfortunately, today, Rosario Sorbella here, and myself. Actually, I'm still listed as a director of BICA Society. I am actually the founding president of BICA Society, and eventually I decided to resign as an officer. So today we need to elect the board of directors and also the advisory board. The board of directors includes David Kelly, who is a software architect, as you see, and he works overtime now and extremely busy, but we have a person who will help him a lot. This is Kirtin Atreides. He will serve as the treasurer of BICA Society, will handle the Bank of America account, which collects all the registration fees, and will help us to pay all expenses. Kirtin is here, you see him. And also nominated is Felix Ramos, who is a doctor of science, not just a PhD, but a doctor. He is also a professor and head of the lab. Well, probably I am missing a lot of his achievements here. Sorry for preparation in a very short time. Now we can vote who is voting, let's say, who doesn't want these three directors to be the next board of directors of BICA Society. Please speak now. Okay, unanimously. So the vote has passed unanimously. The next is advisory board, which I propose to compose as follows. Number one is myself. I remain advisory. But by the way, this is not a position in a BICA Society company, which is a legal entity. There is also a scientific organization, BICA Society, that has its own board. So now we are considering this board. And those people will be an advisory board for BICA Society company, without any legal responsibility for what the company does. And I still want to be here as an advisory. The next I propose still have Rosario Sorbella as an advisory. And finally, Jan Trur, who promised to be here, but for some reason he could not make it. He has a lot, I'm sure he has many hundreds of pages CV, but I just had no time to put it on the screen. So he is a famous professor from Amsterdam, yes, and he agreed to be on our advisory board. The good thing about this person is that he always replies to my email within a minute, no matter when I send it, during the night, during the day, at any time of the year, he always replies, unlike most of other colleagues. So who is against these three candidates as advisory board of BICA Society? Nobody. So the vote has passed unanimously, and we can document it by our video recording. Therefore, we have now two boards. One is the board of directors, which itself will decide who is going to be the president, but it is already decided, I guess. And the advisory board, I am not sure that it has any structure, just a list of advisories. So this concludes our BICA Society election of 2022. The next item on the agenda is, this is wrong order. The next item on the agenda is BICA 2023, and we are going to hear for the presentation of Professor Ting-Tin Liu. I'm spelling your name correctly, sorry.
It's correct.
Oh, thank you. So please share your screen, and
Okay.
or I can do it for you if you like. Please share your screen and show your slides and give us your presentation.
Okay. Where's my screen?
Oh, there must be a button at the bottom somewhere.
Yeah. I found that sharing button, but I cannot find my PPT. Wait.
Not allowed to share the screen. Maybe I can show you your slide.
Yeah. I found it.
Okay, great.
Hi everyone. My name is Ting-Tin Liu. I'm from College of Science and Technology, Ningbo University. I will do presentation for BICA 2023. The BICA 2023 will be held in Ningbo in September or October. This is our preliminary organization committee. I will be the general chair, and Zhen Liu, co-professor from Ningbo University, will be program chair, and Alexei will be program co-chair. We haven't started to contact the sponsors yet. So the sponsors we have is BICA Society, our college, and you, MEPHI. Sorry, I don't know how to pronounce this.
MIFI.
Okay, MIFI, sorry. And this is the outline of the rest of my presentation. Let's see the Ningbo first. Ningbo is located midway on the eastern coast of China. This is Ningbo, and it is near Shanghai and Hangzhou. So this is Ningbo, this is Shanghai, and this is Hangzhou. Ningbo has international airport and a railway station. So if you want to come to Ningbo, you can fly to Ningbo directly. But if you don't want to fly to Ningbo, you want to fly to Shanghai, that is also okay, because Shanghai to Ningbo is it's very easy from Shanghai to Ningbo. You can take high-speed rail. This is our high-speed rail. It will take you 2 hours from Shanghai to Ningbo. If you take high-speed rail, you will from Shanghai, this is Shanghai, to Hangzhou, and then from Hangzhou to Ningbo. The total route is take 2 hours. The rail starts from 5 a.m. and ends at 9 p.m. You also can take bus. This is the route of the bus. You can see if you take bus, you can from Shanghai to Ningbo directly cross the sea. But it will take you more than 5 hours by bus. If you want to fly to Hangzhou, it is also a very, very beautiful city. You can go to Hangzhou to see it. You also can take high-speed rail from Hangzhou to Ningbo. Is much more shorter than Shanghai. It only takes 1 hour from Hangzhou to Ningbo, and the rail starts from 3 a.m. and ends at 10 p.m. There are a lot of rail from Hangzhou to Ningbo. You can see this schedule. There's a rail at 11:55 and a rail at 11:57. So around 2 to 20 minutes, there's a rail. And if you also can take bus from Hangzhou to Ningbo, it will take you 2 hours, but very cheap, only $5. Ningbo is famous for its business. There are many famous merchants from Ningbo, like Sir Ron Saw. He is a very famous movie model, and Bao Yugang. He is the world lord of ships. He has built the Ningbo University, which Zheng Liu comes from. And in recent times, the city has produced more than 100 national academicians, including Tu Youyou. This is Tu Youyou, the first Chinese Nobel laureate in science. Ningbo has also awarded as Olympic champion city. These are champions. There are 5 champions in 2021 Tokyo Olympic Games. They also come from Ningbo. Ningbo also has lots of tourist attractions like Tianyi Pavilion. This one is one of the world's oldest private libraries. And Dongqian Lake, it is the largest freshwater lake in Zhejiang province. This is my college. You can see from its name, College of Science and Technology Ningbo University. So it is under Ningbo University. It is located in Ningbo, but now it is located in Zixi. We moved to Zixi in 2019. It is 1 hour from Ningbo. Now we have 12,000 students and nearly 600 teaching staffs. This is Ningbo University, the Professor Zheng Liu comes from. It is the key university of Zhejiang province and one of the universities in country's double first-class initiative. There is some information about our research team. Our research team is based on Zhejiang Provincial Key Laboratory, and we are interested in effective computing, which include virtual reality and artificial intelligence. This is one of the experiments we have carried out. In our research team, there are more than 30 people. The team is led by Zheng Liu. He is doctoral supervisor, has conducted international cooperation research with the United Kingdom, South Korea, Taiwan, Malaysia, and Russia. He has published a book about virtual agent. This is his book. And this is me. I'm the master supervisor winner of Ningbo Top Talents Project and published more than 30 journal papers and have conducted some international projects. We also have 5 teachers come from mathematics, electronic, information, physics, and information systems. We have more than 20 graduate students, including 4 PhD students. They are some of our students. So let's say the venue of the event. It may be Golden Port Hotel. This is the out view of the hotel, and you can see this tall building. This is the hotel, and this is the lobby of the hotel. This is the inside of the hotel. A room is around $50 to $70 per night, depends on the exchange rate. So you know the US dollar is very powerful these days. The hotel has very good location. It is in the downtown and very near to the railway station. You can take taxi from the railway station to the hotel by 6 minutes. And it also very near to some tourist attractions like Old Bund. This is Old Bund, only 300 meters from the hotel. You can go there within, I think, 2 to 5 minutes by walk. Oh, sorry, this place is famous for bars and restaurants. It is also very near to Catholic Diocese of Ningbo and to Tianyi Square. This is Tianyi Square. It is famous for shopping. And this is a conference hall of the hotel. There are a lot of size of conference hall. If we need to book a conference hall, we only need to pay for the deposit, 20% deposit 1 month before the event. The conference hall may be big for 100 people or for 70 people, or also may be small for only 30 people. This is the date of the event. It may be in the mid of September or in the mid of October. We haven't decided yet. We will discuss with Alexei to fix the date later. So hope we will have a great event next year. Welcome to Ningbo. Thank you.
Thank you very much, Tim. Now, please, who wants to comment, or because we need to decide now if this is our strategy for the next year, then we commit to it. And well, in particular, we hope that Kirtin will help us to organize it, because if we need to make a deposit in advance, then we need the money before the fees are collected. And so that means, well, maybe they will be collected by that time, who knows? But still we need the money, and it can only come from the account to which the fees are collected. And the only person reachable for us who has access to this account is Kirtin, because David is virtually non-responsive at all. And it depends now. We have to take the risk. We need to trust Kirtin, and we put our fate in his hands. And if he fails us, then we fail. Kirtin, what you say? Do you like the idea of having the next conference in China?
Well, based on the expenses that were shown, then it seems like it's certainly more affordable than doing something in Seattle.
Yes.
That's kind of my baseline of comparison. And yeah, I'm very responsive. I'll respond to something that you send me within 24 hours, if not sooner, as you realized this morning. So we can go over the specifics of the cost of setting everything up. I only knew about coming on the board, but not specifically the treasury part, but I'm fine with helping in that role.
Do you have access to the accounts?
Bank of America account, David was asking about finding a better solution for probably international transfer fee purposes, that sort of thing. So I was looking into some other options that we could use. But if he has the Bank of America account, then I can get access to that from him.
Great. Great. Thank you. So I'm sorry again that David is not here, and he is still the person in charge, so he would give the final word, but I guess it's obvious now. There is no alternative. Felix, what do you say as
well, I think
the new director of BICA Society, one of the three? Yeah.
Okay.
Congratulations, first of all. And congratulations to you, Kirti. Yes.
Thank you.
Okay. In my opinion, it's a good opportunity. However, here in Mexico, we found some funding from companies and some also from the government. So I think it is possible to explore that possibilities in order to reduce, for instance, the cost of this organization. However, I think it's great. It's a good opportunity for us to know, to meet different people, and also for knowing that place that seems to be great. So for me, it's a good opportunity.
Okay, who else wants to comment? Rosario?
I agree, and I think that as Felix told to us, I think that is a very great opportunity to have this close meeting with the Chinese colleague. China, like the other nations, are working a lot about research, and I will be happy to come personally to Ningbo to attend this conference. And
you will? You think you will go there?
Yeah, I want to do all my effort because I never go to China, and this could be a very good opportunity. And I'm pretty sure that Professor Ting with his team will do a great job, and she will find a good opportunity, as Felix told us, to find some support from company or in order to reduce the fee for the attendant, because the idea is to have more people. If we can reduce the amount of money that each person that attend need to pay, it can be a great opportunity, especially after this black period that all of us in the world we have about COVID experience. And I think that is a great rebirth to start again with more power, more fresh energy in this BICA society that's always great to the great jobs of Alexei, connect people from all around the world. This was one of the great points that Alexei pointed out, to connect people that come from different areas, from different places, but with a common goal. And especially in that period, I don't want to do any politician or politics.
We do not, by the way, we do not allow any political statements.
No, I don't want, because the important is research. I want to say this. I don't want to do nothing on this, because in this field, we are all research, all connected, and we need to work all together, because this is our power, working all together for the growing of the research. This is my...
agree more. I wish it was actually in real life, as you say.
Yes, my hope also in real life. We can give our point of view from research that can be reflected in the real world. This is my opinion. I am optimist to find a new age for us. And this... because I am a great friend of Alexei, and I want to be great friend also of our colleague from China and all around the world. Thanks a lot.
Well,
thank
practically
you
speaking,
for your words. Sorry.
Practically speaking as well, then the Chinese government has been historically very interested in getting more research papers, more researchers in attendance, so it seems reasonable to seek some potential funding through them. Does that sound accurate?
They are growing very rapidly in science. China is very
Alexei,
rapid. Yeah.
Alexei, Ricardo want to talk.
Yeah, please, Ricardo, say something.
It's just a question: if this is going to be a hybrid conference again, or it's going to be
yes.
only on site?
Hybrid. There is no other way, because we are not certain about the situation of COVID, situation with the war, and I do not know what to predict in a year from now. Absolutely have no idea. So we commit to a hybrid event. In the worst case scenario, it would be like we have in this year, only local people in Ningbo and the rest participating virtually. But in the best, or in the optimal scenario, we will have a large crowd in that hotel, as always at BICA conference. Yeah, so I'm looking forward to that. And now I have to ask Professor Zhen Liu and Professor Ting, what do you think about this question of possibility of finding the findings from government, from scientific funding agencies, or from any sources in China?
It do have possibilities. Actually, we are planning doing this.
But you are not certain yet, of course.
I cannot totally guarantee.
And this is why we cannot count on it.
But it did has chance that we can do it because I know there is some fund for international conference, but I cannot guarantee I can get this fund from the government.
Is there an application procedure for that?
Yeah. We will apply for it later.
So we need to prepare together and help you to apply for it.
Oh, thank you.
Yeah, I hope you let us know when we need to help. Okay, the time is running. Sorry, what do you say?
And maybe I think Professor Zheng Liu want to say something to you. Professor Zheng Liu, maybe he want to say something to you.
Professor Zheng Liu.
Zheng Liu. Yeah. Maybe he want to say something.
Or maybe you can translate what he says if he does not want to speak English, for example.
Okay, I will ask him. 刘老师，你要说点什么吗？刘老师。
His mic is muted. Oh, this is why. His mic is muted.
I told him.
And, he has no mic. Oh no, his mic is muted, and that's it. I don't know how to help, but I guess the only option would be using a phone. Oh, here, now we can hear you. Okay.
我说一下啊。Okay.
Yeah, we can hear you.
It's a great pleasure that BICC AI 2023 will be held next year. We welcome all the experts to Ningbo. Ningbo is a famous coastal city, and many academic conferences are usually held in Ningbo. I believe that the next year conference will be success. You experts have any question? Let Ting Ting to tell more about the details. 你可以和他们讲一下吧，好吧？
Okay, that's it.
Thank you. Sorry, we are running out of time, and we still have one more item on our agenda of this panel is the BICA Society Awards. And so you might be surprised, but let me give the floor to Felix, and please, Felix, go ahead with the list. And Rosario, or maybe Rosario can share his screen and show us the certificates that he was creating. No.
I can show some certificate because her name are reported only by mail, but I can show.
Yeah. Just show us
better that Felix show
how it looks like.
Okay, just one. Okay, I will do it. Okay, yes, I will do it immediately. 1 second.
Okay.
And okay, I will start, and then I will leave. Okay.
Just share your screen and show it to us.
Yes, 1 second. Okay.
Felix, do you have the list of names?
Yes.
We don't need paper numbers or
titles. Okay. Do you see? Do you see?
Yes, we can see.
Okay.
And the winners.
Okay. I'm proud that.
Go ahead.
Please, Felix.
Okay. The winners for
please,
the Outstanding Research Award are Ting Ting Liu, Luis Adrián Parra,
This is
Peter
surprise.
Rodkin, and Luis Felipe Rodriguez. The
Thank
winners
you.
for this innovative work are Jan Treur, Howard Schneider, Agnes Auguelo. The winners for the Doctoral Consortium are Ivan Rodkin y Herrera Pirova.
Yes.
Yeah, those are the winners. Was difficult to decide the winners, but because most of the work were very, very interesting. So, but it's a decision, and it's our decision. Okay. So, congratulations for all the winners. Very good work, and continue working more hard.
Thank you.
Thank you.
Thank you. Thank you.
Thank you. Thank you to everybody.
Everybody who is awarded will receive the certificate by mail. Oh, sorry, there was the last part of the student award, which was given by our late-breaking participant. And it is a free membership in his company program, which is called First Step in AI, something like that. And it is done for free for 6 months. And he says it has a value of $6,000. I cannot believe it, but this is what he says. And I believe we decided to give it to the 2 students who received the Doctoral Consortium Awards, because it is more like a training program, as I understand, and students are those who need it most. So if I'm not mistaken, then Felix, do you confirm what I'm saying?
Yes, yes.
Okay, so Ivan Rodkin and G. Pirova are the winners of this special award.
Yes.
Congratulations. Okay.
Okay.
Now I give the floor to Felix to conclude and move further.
Okay, we are not concluding. It's just a break, and we restart the presentation. Okay.
Thank you.
Give us 5 minutes.
Okay. Could you send me, Felix? I send you a message.
Yes.
By chat.
Yes. I read it.
Okay. Thank you very much, Felix, and congratulations for your new position. Okay. I am pretty sure.
Congratulations to all the new directors and advisories. Thanks a lot. And
thank you very much. It was a pleasure to meet the new colleague that I never met before, and thanks a lot.
Thank you.
Thank you.
See you soon.
See you soon.
See you.
Okay.
Hopkins University in Baltimore, Maryland, 2012. Thereafter, he joined the National University of Singapore, where he was awarded the Temasek Research Fellowship in 2015 and held co-appointment between the Temasek Laboratories and Singapore Institute of Neurotechnology. In 2019, he joined the Neuromotive Computer Laboratory Intel Labs in Santa Clara, California as a senior research scientist. His research focuses on bio-inspired algorithms
and architectures for visual sensing and computation. Thank you very much, Dr. Gary Orcutt. If you want to share your screen. And start
sure. Let me share my screen here. Are you able to see the front slide now?
Yes. Yes.
Okay, and it appears you can hear me, so I'm good to go, is it? Okay, so let me get started. I'd like to tell you all today about our new chip that we've released in Intel's Neuromorphic Computing Lab. The chip is WEHE2, and tell you a bit about our lab software framework that is well, something we first released over a year ago, but it's kind of an ongoing development effort that we're working on. And together, these two things form some new tools that we think push us into a new era for neuromorphic computing. So starting off with our overall research vision, our vision here is to develop a new programmable computing technology that's inspired by a modern understanding of computation within the brain. So the classic example we use here is the parakeet on the left. You can imagine this bird as a very small, very lightweight, very low power brain, yet it's capable of achieving some pretty remarkable things. It can fly around through completely unknown environments, something it's never seen before. The environment can be dynamically changing, yet it can navigate very efficiently and effectively through that environment, traveling at very high speeds. And it's almost effortless for this bird. Whereas by comparison, something like the quadcopter we're showing in the bottom left there would have to carry a small computer. It would be burning many watts of power and is very limited in what it can do. Often it needs to be pre-trained to fly through an environment, doesn't necessarily handle dynamic environments well, and often they still require infrastructure sensors. And even with all of that, they cannot come anywhere near to matching the kind of speed and agility you might see from the parakeet. So clearly these are two very different computing paradigms. So within the lab, we're looking to see what is it that the brain does so well, and can we exploit our modern understanding of the brain to make new computing technologies, right? But this technology doesn't need to only apply at the very edge, not only to parakeets and things with very small brains that are navigating through these environments, but we can imagine them also, doing some more kind of, let's say, planning type work, maybe taking the place of like a desktop computer here. We've got in the middle of the slide, conventional client computing and edge computing. So maybe something that's not really just a tiny, lightweight, low power brain in a mobile system, but something that's really doing some real computation without going to the robotic side. And even further up than that, we can see these things finding application in data centers. So we'd really like to be able to achieve brain-like efficiency, speed, adaptability, and intelligence over all three of these different ranges, right from the edge to the data center and all the way in between. And we're striving not just to match today's computing technologies, but we really want to be delivering orders of magnitude gains in energy delay product. So the energy delay product is the energy it takes to reach a solution multiplied by the time it takes to get to the solution. So we're looking at orders of 10 to the 4 or higher. Okay. Now, it's a daunting task to try and mimic or emulate what the brain is doing, right? The brain offers a huge space of design exploration that we could follow. I'm not going to go and read off all these different items we have here on the slide. The point is just to show that depending how closely we choose to mimic the brain or how accurately we choose to mimic it, we might choose to implement many of these different features that we have here. But at some point, we've got to say what makes the most sense for what we can implement today in modern silicon, modern CMOS, without going to pains trying to mimic or replicate aspects of the brain that aren't really going to benefit us in silicon. Right, so you can come up with some very exotic and uncommon properties in these things, going as far as autonomous healing and self-growing materials. But we're really sticking to Intel's bread and butter here, which is conventional digital CMOS electronics. Right? So how do we approach such a task? We take this iterative architecture algorithm co-design approach where we have algorithms and software teams, we have our silicon and hardware teams, and they learn from each other, and we iterate both the hardware, and with new hardware we explore new algorithms, and as we're exploring new algorithms we come up with ideas of how to tweak the hardware again. So we have this kind of co-design cycle illustrated in the middle of the slide. There's a decision tree shown on the left for the silicon. Many different decisions we could have made that could have helped us to arrive at different sort of chip implementations. So, I'm not going to go through all of them, but just to read quickly through each one to say, what the thinking is. Do we want to pursue neuroinspiration at all? Do we want to integrate the memory with our compute? Do we want temporal neuron models, which I'll touch on the meaning of that in a moment? Are we going to stick with standard CMOS or go to new, more exotic devices? The one area that we do things a little bit unusually in the Neuromorphic Computing Lab is that we use this asynchronous design style, right? Meaning there's no clock on our chips. The circuits just operate asynchronously. It's still conventional digital CMOS logic, but the design style and the design tools are a bit different. And in fact, we maintain our own tools in-house. We could have decided to integrate analog circuits in the chips, which we didn't. And finally, do we want to support plasticity? So the ability of the chip to learn or modify its configuration on the fly through data that's it's processing. So we kind of followed the decision tree on the left all the way down and arrived at the Luihi chip. But if we'd taken a different decision at any one of these branches in the tree, we would have arrived at a different architecture, right? From anything from a conventional CPU to a GPU to even other neuromorphic architectures, which are, of which there are many that make their own kind of decisions towards the bottom of this tree. On the algorithm side, we explored a very wide range of algorithms from conventional deep learning and backdrop trained algorithms, which are, prevalent in AI today, to some kind of further out, more exciting new ideas in high-dimensional computing and vector symbolic architectures, attractor networks, which cover some of the neural engineering framework field and dynamic neural fields, oscillatory computation, so just having oscillators as the basic unit of computation, many different kind of algorithmic areas that we can look at within the neuromorphic architecture. So at all stages here, we're rigorously benchmarking the results. We're trying to see, how many cycles does it take to, how many cycles does it take for us to reach a good solution? How efficiently does the hardware implement it, and learn from these to improve both the algorithms and the silicon architecture. Okay, so arguably the key differentiator of our chip at a low level is that the neurons that we use have dynamics. So people are very used to in deep learning today the idea of constructing large networks of neurons connected via synapses. But these neurons are what we describe on the left here as artificial stateless neurons, meaning the neuron's output at any point in time is purely a function of its inputs at that point in time. There's no history, right? It doesn't have any dependence on previous inputs. It doesn't have any internal time-varying state. And this is in stark contrast to a spiking neuron, which is on the right-hand side, where it's inherently processing time series data, right? Spikes, ones and zeros coming in over a period of time that affect the internal state of this neuron. And that internal state evolves with some internal dynamics and then produces these output spikes going out towards the right there. So the key differentiator here is that the neuron on the right has some internal time-varying state that evolves according to some dynamics, and its output at any point in time is dependent on not only the current input to the neuron, but also the previous inputs to that neuron. So the neuron has some form of memory inside it. So we could see this as a nonlinear filter. Right? We have chosen the asynchronous design style, as I mentioned before. So if we imagine in this top row here, we have this grid of blocks. Each one of these could be a neuron, and only 4 of these neurons are strongly enough activated that they need to output some data. Right? These 4 neurons can be arbitrated onto a bus, and these 4 pieces of data can be read out very quickly. They don't have to wait for any clock edges. They don't have to wait for any other neurons to be output. They just go straight out. Whereas on the bottom side, if we're in a more typical kind of asynchronous architecture, we'd have to go query all these neurons and sort them to find out which were the most activated. And so reading out all that data is going to add latency in communication. And of course, it costs you in terms of energy as well. Many modern approaches do implement some form of sparsity, but it's usually a very rigid sparsity, meaning if we imagine that each one of these squares here is, again, a neuron, we might enforce some sparsity so that we're only ever querying, say, the black and red dots, but even within the black and red dots, there may be only very few red dots that we want to read out. So the take-home message from the slide is that in the face of sparsity, asynchronous communication is very fast and efficient. And so our algorithm and our architecture that we implement are all targeting sparsity. Okay, so these design decisions, they lead us to a new class of computer architecture. I think we're all familiar with the far left standard CPU architecture, right? So sequential thread, sequential, sequence of instructions that are being implemented at very high speed on the CPU. More recently, people have been shifting towards parallel computing. These would be more like your GPUs. And instead of writing a sequence of instructions to be executed, you train a model offline using very large labeled data sets. So this is a big move towards parallel computation, but neuromorphic computing on the far right there takes things a few steps further in a few of the areas. So one is the ability to learn on the fly through neuron firing rules. So this means learning happening within the chip online, right? Meaning not offline with labeled data, but online while new data is being processed. Asynchronous event-based spike communication. This is just a design style choice that we've made. But it's highly, highly parallel, but with very sparse compute. So many parallel elements, each of which can be doing a different thing, but only very few of them are active at any point in time, right? Which is very different to having these very large, dense, say, matrix vector multiplications that you would find in many deep learning architectures. So we realized all of this in Luihi, which was the first chip that we released. This is, end of 2017, early 2018. Some of the key properties to highlight again here: the compute and memory are integrated, so all the memory for the chip is inside the cores themselves. There's no separate DRAM. We have these temporal neuron models, so the neuron models with internal time-varying state. The neurons communicate with each other with spike-based communication, so very sparse communication. Only when a neuron is very strongly activated will it then output some data and reset. The connectivity between the neurons is sparse as well. The cores have this ability to learn on chip, and it's all just fully asynchronous, right? So it's still digital, but fully asynchronous implementation. Something that we work a lot on in the lab, something that maybe many teams find, a bit difficult, but our team's got a lot of experience with this, and we actually find it to be a very productive design style for us. Perhaps more surprisingly is what is not included in the chip, which are there are no floating point numbers anywhere in the chip. There are no multiply accumulators anywhere in the chip, and there's no off-chip DRAM. And so these are things that are kind of fundamental to deep learning hardware, and yet that we don't have in our neuromorphic chip. So we've learned a lot from this chip over the last few years. We built a large community. Over, I believe it's 180 different research teams from around the world and are part of Intel Neuromorphic Research Community. We have Fortune 500 companies, government labs, but mostly academic researchers and academic labs from around the world. We've built edge-based systems, interface to dynamic vision sensors. We've built large rack scale systems with hundreds of chips. We've had NASA send, in collaboration with the Air Force here in the US, send Luihi up into space, into orbit, and planning to do so again. We've generated a wide range of results on many, many different tasks that I'm going to touch on in the next few slides. So we really feel like we've made significant progress over these last few years and learned a lot about the technology. And we think Luihi's really confirmed the value of this direction that we've taken. Some of the examples shown here, this is actually me on the top left swinging my arm around in front of the sensor. We showed that we can do this kind of gesture learning or gesture recognition at very low power with a dynamic vision sensor coupled to the Luihi chip. So this is operating on about 60 milliwatts total power, only 15 milliwatts of which is dynamic, while detecting these 10 different gestures and classifying them in real time. More recently, that work's been extended to allow online learning of new gestures on the chip, again, just while observing somebody performing them. In the bottom left, we have adaptive robotic arm control. The task here, this is just in simulation. You see the task being performed. There's a robotic arm that must be controlled to just move from point to point. And it's a pretty simple task in the absence of any load. But the moment the robotic arm has to pick up a weight of some kind, there's suddenly this large weight on the end or mass on the end of the arm, and you need to change your controller or adapt your controller to counteract that weight. So with our chip, we're able to operate at 40x lower power than the GPU, and we're able to adapt 50% faster. Combinatorial optimization is another one that I'm going to touch on in a few of the future slides. But the take-home message just from this slide on that is that we're able to achieve thousands of times lower energy than a conventional CPU and find solutions many times faster, in this case 44 times faster for, I believe this is a Sudoku. We had some results in olfaction-inspired odor recognition and learning. So how do you learn to recognize new odors when you've only been presented with them once or twice? And odors are just inherently a very kind of noisy signal. And we're able to show 3,000 times more data efficient learning than a deep autoencoder. We also have a number of efforts ongoing in scene understanding, so visual scene understanding, tracking head motions, object recognition, learning at very low power, and doing SLAM 100x lower power than versus a CPU. These results that I'm mentioning here are all summarized in a paper that we released last year, the citation for which is at the bottom of this slide. So part of the point of this research effort at building this community is to find out what the technology is good for, and of course along the way, figure out what it's not good for. So this is one of the take-home plots from that paper, again cited just at the bottom of the page here, where we try to measure for a wide variety of tasks how well we're performing using the energy delay product. So energy, we always compute a ratio, the energy that it took our chip to find a solution versus the energy that it took a competing approach. So it's always a comparison point between our chip versus some other solution. So the horizontal axis here, the further you move to the right, the more advantage Louis has on a specific task. And conversely, of course, the further you are to the left, the less advantage we have compared to conventional solutions. Similarly, for the vertical axis, that's the solution time ratio. So how quickly can we find a solution? The higher up we are within this plot, the quicker Louis is at finding a solution versus a conventional approach, and the lower we are, the worse. So we typically multiply these two ratios together to get an energy delay product. And so the parity line is shown by this dashed line, oblique line going across the plot. Anything that is above or to the right of this line is somewhere where Louis, our chip, it has a better energy delay product than competing solutions. And anything that's below it, we're performing worse. So ideally, we'd love to be at the top right of this plot for everything. But in practice, of course, we see results spread out all over the place. But we can see some trends already if we look at this, this plot. First of all, we see that feed-forward deep neural networks are really the worst class for us. They offer the least gains, or in some cases, no gains at all for Louis. But this is not too surprising. We're not out to make a better deep neural network accelerator than all the other companies that are out there playing that game. We're hoping to unlock, some new values, some new kind of computational capabilities that aren't offered by those types of accelerators. With very broad strokes, we can say that the networks in the top right of this plot where we do see great advantage are recurrent networks. There's probably a bit of an oversimplification because these networks are spanning a wide variety of tasks. You can see them on the right there. Sequential MNIST, the adaptive robotic arm controller. There's some sparse coding problems, there's SLAM problems, k-nearest neighbor problems, graph search problems, constraint satisfaction problems, just a very wide range of tasks that we're able to tackle. The common property between them is that they don't have a predictable feed-forward type of architecture. They have the ability for any neuron in the network to connect to any other neuron, which we dub here as a recurrent network. If we zoom far in on the top right of this plot, we see that the best examples we have today are optimization tasks. So three of the main ones here is what are the best features, or what are the features, sorry, that best explain some sensory input that I'm seeing at the moment. So we get some input from a sensor, we have a dictionary of possible elements that could be used to describe what we're seeing, and we want to pick out which are the best ones that most closely describe that sensory stimulus. Another is what is the shortest path to my goal? Again, this is kind of a graph where anything can be connected to anything. It's a kind of recurrent network. We want to know what's the shortest path between 2 points within this graph. Or what is the shortest path while visiting each of a number of waypoints exactly once? It's another variation of the graph search problem. So a key insight here, again, I'd mentioned that the recurrent networks are the area that we see the biggest advantage. So our neuromorphic networks, they have this interconnection between neurons in any directions, and they kind of just iterate towards a solution. We find that they can do so very efficiently and very quickly. And this is very different to what you see in conventional deep networks, which are typically feed forward. So they require a different architecture, right? The feed-forward networks, you can accurately predict which neurons need to be updated when, because you know when you're going to feed data in and you know how the data is going to flow through the network. But if they don't find a good solution, they don't have a chance to continue to continue iterating to find a better solution. Right, where the neuromorphic network on the right can continue iterating and finding better and better solutions, basically performing gradient descent until it finds a satisfactory solution. Okay, so this slide kind of summarizes it again. We can imagine that we have a network on the right that's a recurrent network. Things are all connected to each other. But the dynamics of the network are set up in such a way that the network is always forced to move down a gradient. Right? The neural dynamics descend some gradient of the problem that we're trying to solve. So we can imagine that we're moving down this gradient, but the problem is it's inherently noisy. Our chip it's very low precision, fixed precision throughout the chip, and there are a lot of random noise sources within the chip itself that we exploit and put in there intentionally. And together this can give us a form of stochastic gradient descent where we can descend down a gradient, but if we hit a local minimum, as shown here, we still have the ability to use the stochasticity to get kicked out of it and eventually traverse down to an even better solution. Some very exciting work that we've been seeing here is that Louis has been shown to outperform leading optimization solvers by orders of magnitude. On the left, we have the example of Kubo, quadratic unconstrained binary optimization. Here, the task is to find the maximum independent set in the set of vertices. And it's a very interesting problem because it's the target of current state-of-the-art quantum annealing approaches. And it's an NP-hard problem. So people are going after this with quantum computing technology. It's NP-hard. But today we can solve these types of problems on Louis at orders of magnitude more efficiently than is being done with a CPU. On the right, we have an integer linear programming task. This is a train scheduling problem that Deutsche Bahn was tackling. So you can imagine you've got to figure out how to schedule all the trains in your network subject to many constraints of how trains might move and how they can't crash into each other and customer demand. So something that has large-scale real-world use. And you can imagine this being applicable to many other tasks as well, right? So not just how do you deploy trains on the train network, but all kinds of resource allocation tasks from warehouses to production lines to, I'm sure you can imagine, military applications and many others. And here again, Louis is performing, in this case, 5 orders of magnitude better on the energy delay product than a conventional CPU with a state-of-the-art solver running on it. So we think that there's some really promising results here. We've gained a lot of understanding of the technology, and we're now kind of ready to take the next step. We believe we're moving into a new era of neuromorphic computing. So the computational value there has been proven. We know we can make these kinds of things with today's manufacturing tech at Intel, but we believe it motivates a new computational paradigm, right? So cheap and continuous optimization is one area that we are seeing, very large gains for us. We've seen many successful learning algorithms, but this is still an area I'd say we need to explore a bit further. Most of them being quite shallow learning algorithms on the chip, not really training very large, deep networks online at least. And the types of applications we're going after are things that are power constrained, latency constrained. We're processing real-time signals. So imagine say, a robotics application, we have sensory data coming in real time. This is something where you want to be processing data as it's arriving as quickly as possible, right? So low latency, processing real-time signals. It's power constrained. Often, these robots are carrying batteries and so forth that need to power them. They may be moving into new environments or changing environments. So, there might be some slowly evolving structure to the problem that you're solving that can benefit from some shallow learning, right? So learning new objects in the environment, for example. But you can always apply deep learning initially to give you a starting point. So offline on a GPU, you can train a model, deploy it to our chip, and then have the chip learn online from there forward. And so we should take a moment here to just recognize how this is different from, say, a GPU type of architecture where they really excel at batch processing. So if you have a real world signal that you want to react to with low latency, you don't really want to be waiting until you've batched 100 signals and then processing them in a large chunk, right? You want to say, I don't need to process 100 at a time. I need to process one at a time, and I need to do it very quickly. So it's a bit of a different, computational paradigm there. Okay. There are, however, challenges and headwinds. First of all, we do have a pretty high cost for our chips. The chips themselves integrate all memory into the cores, and adding that memory takes up silicon area and makes it expensive, right? So we don't have DRAM, we have on-chip SRAMs, and that means that our chips are going to be pricey. We still need more maturity in the algorithms and programming models. So there are many exciting algorithmic approaches that have been shown, but we need some way to kind of pull them together and have programming models that we can introduce to new users to get them started. And this really ties into the software convergence problem there. A lot of people in the field so far are doing one-off solutions that just show, how good their particular application is, but they're not really able to transfer it or release it to other labs for them to use or combine it with work that other people are doing, because everyone's kind of writing their own piece of software. So what we hope to drive, moving forward is convergence and getting everyone behind one piece of software, even if they're doing completely different things, right? Someone who's doing audio processing and vision processing, they should be able to combine it in the same robot without requiring completely different software frameworks. So we're moving towards trying to solve these problems. One thing is that we've recently released in about the last year a greatly improved Loihi 2 chip. It's about half the area of our first Loihi chip. It's using an early pre-production version of the Intel 4 process. Yet it makes many improvements over the first chip. And so despite being half the size, it's about 10x faster, the circuits themselves. There's a combination of process manufacturing advantages and architecture and design changes that we've made. We've improved the capacity. So despite, again, being half the size, we have 8x more neurons per chip, and just far better scaling and integration. So even on our first chips, we were able to combine many chips into a single system through kind of a 2D mesh of chips. We've now expanded that to a 3D mesh of chips. The chips speak with much higher bandwidth with each other. They also require less bandwidth because we implement greater compression and new I/O protocols between the chips. We've also implemented 10 gig Ethernet, so a way to just get a lot of data in and out of the chip really quickly. Otherwise, some aspects of the chips, the Loihi 2 chip, remain pretty similar to Loihi 1. It's a chip consisting of 128 neuromorphic cores, each implementing many neurons, and they communicate with other chips nearby using parallel off-chip interfaces, which allow you to scale up from a single chip to large data center type systems with many chips. And each chip has a number of microprocessor cores on chip. These handle things like data I/O to the rest of the cores. They can monitor and configure the network. Just do any kind of maintenance task. You can even imagine, say, a neurogenesis type algorithm where neurons are being added to a network and the structure of the network is evolving over time under control of C code running on one of these microprocessor cores. Because the SRAM on chip is pretty expensive, we've put a lot of effort into making sure we get the absolute most out of the SRAM that we possibly can. So this is done in two different ways with Loihi 2 now. One is that the SRAM is shared between all the different features. So to take a simplistic view, if we imagine that a network consists of neurons and synapses, in Loihi 1, you had a fixed amount of memory for neurons and a fixed amount of memory for synapses. In Loihi 2, they can share memory. So if you have a particular model that is skewed very heavily towards synapses, you can just allocate more memory to the synapses and less to the neurons, and vice versa. So there's a lot more flexibility in how you allocate the memory, but there's also far greater ability to compress data in memory, right? So our neuron state is typically compressed by 4 times now in Luigi 2 versus Luigi 1, axon writing by 256 times. But really, most of the compression happens in the synaptic connectivity. We have a number of different features for compressing synapses, from built-in support for convolutional kernels to factorized weight matrices to procedurally generated pseudostochastic lists of weights in each core. Luigi 1 also used binary spikes with leaky integrated phi neuron models, which means we could only have 1-bit spikes, and we had a very rigid neuron model. The leaky integrated phi model. Luigi 2 generalizes this concept. So we have generalized spikes that can now carry a payload between neurons, and the neurons themselves are just governed by some microcode that the user writes themselves. And this means that the user has the freedom to write kind of an almost arbitrary neuron model based on what it is that they need. Right, so we've generalized the spikes, we've generalized the neuron model, we've made sure you can compress the memory far more, we've added flexibility in how you allocate the memory, and taken advantage of the Intel 4 pre-production technology to arrive at Luigi 2. This is just an image of the chip itself here. This would be the chip in the package on the top left. This is just kind of the die shown on someone's fingertip. This is about 4 millimeters by 8 millimeters in total. And of course, we've been putting these chips down into systems and implementing some workloads on them and characterizing them. And overall, not surprisingly, we see that Luigi 2 does offer us significant advantages over Luigi 1. Circuits are quite a bit faster for neurons and synapses. Our time steps can advance much faster, so that's just a measure of how quickly we can process data, and we're able to lower the energy quite a bit versus the first Luigi chip. We are starting to release systems to people. You can see here Gulch at the top there. That's kind of a large single chip system just for kind of basic bring up, but we've been starting to expose those for the last year or so. And we have point systems at the moment, at the bottom left, which are 8 chips in a single small board. It's about the length of a credit card squared that our INRC users will have access to. Deep learning hasn't been the greatest area for us with Luigi, but it is one of the areas where we can just take a model off the shelf and implement it on Luigi 2 to get an idea of the advantages that we're seeing. We're seeing pretty significant advantages over the first Luigi chip. We'd implemented the simple pilot net model on Luigi 1. The task here is simply to estimate steering wheel angle from dashboard video. So the Luigi 1 numbers are shown in the very left column here. We implemented the exact same model, right? It's the equivalent model on Luigi 2. So it achieves the exact same mean square error, spike for spike, neuron for neuron, it's the same. Yet we're able to shrink the model by about 5 times in the number of cores it requires. We're able to drop the latency down by a factor of about 6. And we're able to increase the throughput by a factor of about 6 too. We're also able to lower the total energy by a factor of 6. This is a pretty good gain for Luigi 2, but this is just implementing the exact same Luigi 1 model on the new architecture. Luigi 2 includes a number of new features that we can exploit as well, the graded spikes, programmable neuron models, and so forth, which allow to implement models that Luigi 1 cannot. So on the far right here, we see the advantage of trying to exploit those models, those properties. We see by exploiting them, we're able to drop our mean square error down by about 30% over what we're achieving with Luigi 1, while almost doubling our efficiency and doubling our throughput again. So this is a very early example task that we're performing on the chip, but we're very encouraged by it. There's a wide range of exploration that we can explore now based on the new programmable neuron models. We published a paper last year. Anyone can look at it if they're interested in seeing the kind of things we've been looking at doing. For example, resonating phi neurons. This is a totally different type of neuron model where the neurons now have some complex, time-varying oscillatory internal state. And we can use that to implement a type of frequency filter. And using these frequency filters, we can do things like spectral decomposition of an audio chirp on the right here. So you can imagine approximating the short time Fourier transform with a bank of these neurons, all with different resonant frequencies. And you can use these filters to apply some energy-based optical flow models to dynamic vision sensor data. So this is another one of the tasks we presented there. Optical flow for event-based cameras. So we have an event-based camera producing data coming into our chip that we can process with these resonant fine neurons. And if we arrange them all correctly, according to some, so this is theory that came out in about the 80s, but we're able to do it very efficiently on our chip, and we're able to show that we could achieve better accuracy than state-of-the-art deep learning approaches are achieving on these event-based camera optical flow tasks, while requiring about 90x fewer ops, fewer operations, to compute the solution. So we think these are very exciting areas for us to look into, moving forwards. So I've touched a bit there on the headwinds that we saw. I mentioned that we see a headwind in the costs of silicon because we have this on-chip memory. I described a bit about the things we're doing to try to compress that memory and make our allocation of it more flexible. We do need maturity as well on the algorithm side. I've described a little bit about some of the exciting new features we put on the chip and some of the algorithms we're starting to look at. But I'd mentioned how a lot of this really ties into having convergence around a common software framework, something that everyone in the community can get behind. And so our proposed solution to this is Lava. It's a new software framework for neuromorphic computing. It's not so new anymore. We've been talking about it for a year plus now. But it's something that we believe can really pull together a lot of different aspects, within the community, and make it far easier for people to share code with each other, publish their results as kind of modules that can be reused by other teams, and build up to far more complex applications by picking and using, pieces of code from different people. So our vision here is really just enable mainstream adoption of neuromorphic technologies. Lava it's an open source software framework. We've been very careful not to, put Intel's name into the name anywhere there. The idea is that we're hoping that the community will get behind this and take some ownership of it and contribute towards its development. We're of course getting the ball rolling, putting significant effort within the team ourselves here into getting Lava off the ground. And so it's a combination of two things. One, it's software tools for productive development environment, but also, through design of the software environment, we have the ability to kind of, so let's say manipulate a bit how we want people to think about programming a neuromorphic device. And it's something that's absent today. The easy thing for people to do is to take a deep neural network off the shelf, standard feed-forward network, and try and run that on the chip. And it's something we support through the tools and something that can be done, but it's just not a strong point for us. So we see the need to kind of change people's thinking about how they should approach programming a neuromorphic chip. So some of the key attributes of Lava, which I'll dive into in a moment here, are event-based communication. So there's kind of the sparse communication that's very event-based, so it's not necessarily predictable or on a predictable schedule. And this communication is happening between many different processes that are operating in parallel. You can imagine how this translates to the chip, where we have many neurons that are all operating in parallel, communicating with each other in an event-based manner. And it's a multi-paradigm, multi-abstraction, multi-platform software framework. And I'm going to touch on what those three things mean in the next few slides. Again, it's open source, permissive licensing for all of the core components. Anyone can come in and use it. You do require a special agreement with us to be able to run it on our specific hardware, right, on our Luigi chips. But it also allows you to, the multi-platform part here, is it allows you to run it on a standard CPU or GPU as well, which means that we kind of open the door for people who don't have access to our chips to do their own software and algorithm development. Furthermore, it is so open that other neuromorphic computing labs who are developing their own hardware are even free to come in and write the support to add their hardware as the back end. And so kind of the ultimate dream is that you'd be able to write some kind of module that you've written it in the right way, and then just by changing a flag somewhere, you can make it run on either a CPU, GPU, our hardware, or maybe even someone else's hardware that they've put in. I won't go too much through the table on the right there, other than just to say that we looked at a number of other software frameworks that were out there, including our own previous software framework, which was this NX SDK here. And we just, with each one, we're able to kind of pick some holes in it. And Lava is the solution that we feel covers all the points that we needed to cover with this new software framework. Yeah, so it's multi-paradigm. So we're not saying that there's only one way that you can use a neuromorphic architecture. So we're targeting things like the optimization approaches that I've shown you on the previous slides. Neural attractors, we have many people working in the lab with this at the moment. Julia Sandomierskaya has a lot of research happening at ETH Zurich there. So I've got some notifications popping up here. Yeah, so she's done a lot of work on dynamic neural fields. So we have software libraries for neural attractors being built into Lava, software libraries for optimization being built into Lava, software libraries for deep learning built into Lava, and even vector symbolic architectures. We have some researchers with us from the Redwood Center for Neuroscience at Berkeley, who've done a lot of good recent theoretical work on VSAs. So you can expect to see within Lava software libraries for all these different paradigms, different ways of computing. It's also multi-abstraction. So you can imagine that some people really want to dig into the details. They want to write their own details of how one small part of a neuron model might work. But other people just want to use the technology, right? They just want a prepackaged neuron model that they can take home and just use off the shelf. Some people don't even want to deal with that, right? They say, I want to build a network of these neurons, and yeah, just give me the pieces I need. I'll build a network and describe the connectivity myself. And there might be people at an even higher level than that say, I don't really care that these things are neurons. I just want a module that does some block of computation for me. I want a network that optimizes this class of problem, and I don't want to think about the fact that it consists of neurons and synapses and all these details. And people might even go a level above that and say, well, I want some model that combines many of these different properties in a single module. So I want to optimize my path to some location and then control the robot to get there. And that can just be presented as a prepackaged module without people worrying about what the bits and pieces underlying it are. So I hope we can expose all these different levels of abstraction. Multi-platform is very important to us. Not only the ability to have different devices that can talk to each other, right? A single system that could consist of CPU, GPU, FPGA, Luigi chips, other things that you might imagine, all communicating to each other through the Lava software framework, but also just the ability for someone to be able to switch from one hardware back end to another, right? So, some PhD student in the lab somewhere has a good idea of something he wants to develop, but he doesn't have access to our chips. So he wants to develop on a CPU or GPU or whatever is available to him. And so it's important to us that people can develop at a kind of more abstract level, but then really, once they feel they've got something good, obviously we highly encourage them to run it on our chips, because we feel that, that specific hardware will give them a real performance advantage. Okay, of course, CPU only if you're just wanting to do some offline kind of algorithm exploration and prototyping. And so we've released a number of different early versions of Lava so far over about the last year. Most recently, we've added support for Luigi 2 as we released it, and fully automated compilation for the chip, and the ability to program different parts of the chip using either Python or C or both. Support for the new microcode programmable neuron models, synaptic plasticity, and just really extended our documentation, high-level tutorials for it. In the very near term, you can expect us to have full Luigi 1 and 2 support, and extended algorithm libraries for the deep learning, optimization, dynamic neural fields, and vector symbolic architecture work that I was describing before. So overall, just to re-emphasize, we really see the ability to apply this type of technology at multiple different levels here. We've come across many different algorithms that we see great promise in. We've built our own systems with Luigi 1 from single chip up to hundreds of chips. We see ourselves, of course, doing the same for Luigi 2. We see the ability to even have just IP blocks that can be built into other chips, right? We have currently the Louis and Louis 2 chips each have 128 neuron cores, but you could imagine solving a problem with only a few neuron cores. In fact, you can, with some audio problems, get away with just 1 or 2 cores. So you can imagine implementing those as kind of side IP on another chip for processing. As we scale up, you can imagine maybe edge co-processors, processing camera feed, something like that, maybe being carried by a robot or a UAV, so helping to do some sensory processing, decision-making and optimization, and maybe some motor control, or scaling up all the way. We've published some K-nearest neighbor recommendation system type approaches that would be run in a data center. We believe we've kind of brought together, through the community that we've been building, Intel Neuromorphic Research Community, many people showing these exciting results. We've got we're on the verge of this new software framework that's pulling a lot of it together. And we've taken what we've learned over the last few years and put it into the Louis 2 chip. A number of new features that have really, blown wide open this exploration space that we have ahead of us. And we think is, going to lead to some exciting things in the near future. So with that, I'll conclude this part of the talk. I'm happy to take some questions. I will highlight at the bottom there, if you found any of this interesting, you'd like to get involved, find out more, you can email inrc_interest@intel.com to get more information. We have a number of different tiers. Simply reaching out can get you on some of our mailing lists, get you access to some more of our information. But if you're interested in actually getting access to our hardware and software and chips and doing something there yourself, we have kind of additional levels of engagement. We run workshops, regular talks, and trying to build this, community and get people to share results and come together there. So please, get involved if you're interested. If you liked what you saw about Lava, again, it's completely open source. You can visit the link there down the bottom to get involved, see what we're doing, download it, and try it out for yourself.
Thank you very much, Doctor. If you have some questions, please.
I have a question.
Hello, I heard someone say they have a question, but I didn't hear anything afterwards.
Okay, can you hear him now?
Can you hear me?
I hear you now.
Okay. Well, this is Ricardo Goodwin from University of Campinas in Brazil. And I'd like to know how is the pathway for getting access to this technology and trying to use it in experiments? Is there some university relationship kind of programs that we could have this chip, or we have to buy it? What are the pathways for getting access to this technology?
Yeah, so we're building that Intel Neuromorphic Research Community that I mentioned. If you reach out to this email address down below, they can get you started with access. We don't sell these chips. We're not at the product stage yet. This is a research processor. So we provide access to people through a few different ways. Our preference is cloud access. So we can give you remote access to run on our systems, and that just allows us to maintain the systems and share the systems between many users. And of course, we have some more control over the software environment to keep things stable. But as soon as people, can show us that they're getting some interesting results, we're happy to send hardware along as well. So we've provided hardware to many labs. We do it under typically a loan agreement, a bailment agreement. So again, it's not something where there's any kind of purchase or money changing hands. It's something where we see, hey, there's interesting results here. Let's get these people some chips to work with. But it's typically motivated by having some results in order or by a need of the project, right? If inherently you need chips in the lab because you need to process some signals in real time, or you're doing some robotics work, and then there's a clear reason why the cloud is not good enough.
Yeah, my idea is to present it to my students and give it to them and see what they can do using it. Do you think it's a good pathway for trying?
Well, I think we'd encourage it, but I'd still push them towards the cloud access route. We can give people remote access to run things, and it just takes a lot of the difficulty out of physical hardware, right? Getting large quantities for teaching is maybe problematic. It's something we can do, but throughout the community, we do have quite high demand for these, and we are kind of manufacturing them not with like a production scale. So our quantities are limited.
Okay, thank you.
Is there any other question?
Yes, I have a question about this.
Go ahead, please.
Yeah, thank you. Thank you for the talk. I have a question about physical neurons unlocking. Can we run multiple neurons, I mean abstract neurons, on one physical neuron? Or we have a one-to-one direct connection between physical and programmable model?
Yeah, no, we digital CMOS is very fast, so we use time multiplexing. So within a core, it's reusing the hardware. When we say you can implement up to 8,000 neurons on a core, we're not saying that there are 8,000 neuron circuits on a core. What we're saying is that you're going to start running into the memory capacity limits of the core for holding the states and the models of those neurons. So the answer is yes, you can have multiple different neurons. You can even have multiple different neurons with different neuron models running on the same core, and that means they are using the same hardware. They're not separate physical circuits for each neuron.
Thank you.
Thank you. Is there any other question? No? Okay. Thank you, Dr. Rockhart. And we continue with the schedule of the meetings. Thank you very much.
Thanks very much for having me.
Good day. My name is Oscar. I will be the chairman during this presentation block. And we shall start with Maxine. Is there?
Yes, I'm there.
You can share your screen. Okay, you have 15 minutes to present your work, followed by 5 minutes to questions from the audience. You can start. You can begin.
Yes, thank you. Good morning, dear colleagues. My name is Maxim Skorohodov. I work in National Research Center Kurchatov Institute, Moscow, Russia, and I present to you our work, Neural Network Method for Determining the Direction of a Person's Gaze based on web camera image analysis. We define the next problem in the process of controlling a robot using voice commands. When the operator observes the environment of the robot, some ambiguity arises in the robot interpretation of the operator's command to move to certain objects. One way of minimizing this ambiguity is to use information about the direction of the operator gaze to improve the accuracy of the voice control systems. Voice command examples: robot move there, robot come to that human, robot move to that tree. The purposes of our work was to create an efficient method for determining the direction of gaze from the web camera data for implementation in the interface of the robotic platform control system in order to minimize voice control ambiguities. We set the next tasks: creation of original data set for model training, development of neural network model for gaze estimation, and implementation of model interface of the robotic platform control system. Related works. Currently, there are special hardware, software systems, and software methods for determining the gaze direction. An example of the hardware system is Tobii eye tracker. Another hardware software systems use Kinect or special tracking glasses or mobile device cameras. Software methods are based on the analysis of web camera data. One of these methods uses pupil detection and mouse cursor data for gaze estimation by regression analysis. Another method applies a convolutional neural network analysis with the detection of facial landmarks and spatial normalization. Hardware-software systems like Tobii eye tracker, Kinect, or special tracking glasses are expensive. A solution based on the analysis of web camera data use additional information that is not required for the robot control tasks. The first is data collected during this work. The collected data set consists of frames from the web camera. The frames match to coordinates in pixels of the position on the monitor screen the participants were asked to look at. The second is the open source dataset WebGazer. It includes the data taken from 51 participants, video recordings from the camera and monitor screen, information about the movements and clicks on the mouse cursor, the position of the gaze predicted by a Tobii device. Also, the authors provide a program code. It splits video recordings into images and two-dimensional coordinates of points in pixel on the monitor screen. Thus, we prepare two datasets. The first is our dataset. It contains about 40,000 frames, and the second is open source dataset WebGazer. It contains about 400,000 frames. Determining the direction of a person's gaze realizes according to the following concept. The web camera image is processed by MediaPipe library. Processed data is fed to neural network model input. The neural network model predicts coordinates and pixels on the monitor screen. Image processing based on MediaPipe library. Web camera images are processed by off-the-shelf convolutional neural networks from open source library MediaPipe. We use MediaPipe face mesh and MediaPipe iris to detect face and eye meshes. The first stage is face mesh processing. For 168 3D face key points have been defined by convolutional neural network MediaPipe face mesh. The second stage is eye region processing. Two eye regions of interest have been defined by face key points. The third stage is eye mesh processing. 71 3D key points have been defined by convolutional neural network MediaPipe iris. In total, 6 models were trained, fully connected and convolutional, each with all 3 output layer types. The fully connected model contains 3 input types. The face mesh input and eye mesh input are processed by fully connected layers. The convolutional model contains 5 input types. Additional, the eye region inputs are processed by convolutional layers. Coordinates prediction. 3 neural network models have been developed to predict coordinates. The first is only X coordinate has been predicted. The second model is only Y coordinate has been predicted. And the first is both X and Y coordinates have been predicted. The first and the second models' prediction accuracy is jointly evaluated. For model quality estimation, we use Euclidean distance L2 metric. In the table, L2 errors has been depicted for each of model types. Using 2 convolutional models allows to get minimal error of 104 pixels. One of these models predicts only X coordinate and another predicts only Y coordinate. The models were implemented into the voice control system of mobile robot. The web camera image is processed and fed to the neural network model input layer. The neural network model predicts the gaze direction. The robot control system compares the gaze direction and the observed environment and generates the correct command. In case robot move to that tree, the choice of specific tree will be carried out according to the gaze direction. The data set was collected. It consists of process images in the form of face mesh vectors, eye mesh vectors, extracted eye images, and two-dimensional coordinates of point in pixels. 6 types of model different in architecture and output types were trained and evaluated. During evaluation, the model's smallest error of 104 pixels was identified. The trained models were implemented into the voice control system of the mobile robot. It allows reducing the ambiguity in the commands of movement to objects. Acknowledgements. This work has been supported by Insight grant of National Research Center Kurchatov Institute and carried out using computing resource of the Federal Collective Usage Center complex for simulation and data processing for mega science facilities at National Research Center Kurchatov Institute. Thank you for attention.
Thanks, Maxi. Now, if one of the audience had a question, please raise your hand.
Hi. I was wondering how sensitive is this methodology depending on the camera position, the web camera position. For example, it can be on the top, it can be on the right, it can be on the left side of your monitor. Did you try these different positions, or you just use the fixed position for all the experiments?
Okay, we use fixed position and fixed position and fixed light during data collection and during experiment.
Do you think that, for example, putting the camera in a different position will give you different kinds of results, or you expect to have the same kind of results?
Could you repeat, please?
Depending on if you put the camera in different positions, for example, on the left or on the right, do you expect to have the same kind of results, or do you expect to retrain all the network depending on the position that you put your camera? Did you understand the question?
No, no, sorry.
Okay, no problem.
Okay, another question? Good. Thanks, Maxi, for your presentation.
Thank you for watching.
Now we shall start with Julia, Pim, and Jen. Is there in?
Yes, hello, I'm here.
Okay.
Pim.
Yeah, you have 15 minutes to present your work, and followed by 5 minutes to questions from the audience.
Yeah, I will.
You can begin.
Can you guys see my screen?
Yes.
Okay, perfect. Hi everybody, I'm Pim. I'm from the Vrije Universiteit Amsterdam. And we published a paper for BICA for a master's course. And the paper is called A Second Order Adaptive Network Model for connecting social media platforms and users through bonding by faked homophily. This is done by me, by Julia, and by Professor Jan Treur. So it doesn't move. Yeah. So imagine it's a cold, dark winter. I'm not sure how that is in Guadalajara, but here in the Netherlands we have cold, dark winters. You turn on your smartphone and you log into Netflix, and before you know it, they pull you right in, and you waste your entire day watching series or movies. So we focused on this phenomena of media and social media platforms. So for instance, Netflix or YouTube, who are doing a very good job of their content delivery matching the user, because you want to give people what they want for better retention. We hypothesized that this is done by faking homophily. Homophily is the process of people bonding through similarity. So for instance, we can find this in everyday life. We can see it in friendships, colleague bonds, marriage, etc. Because birds of the same feather flock together. So similarity breeds some form of connection. This feature one could also use and fake it. So for instance, if you like someone, but they have, for instance, they have a certain hobby that you don't like, you can fake that you like it to still create this homophily and still create this connection. For this paper, our main source was Mental Models and Their Dynamics, Adaptation and Control, which is a book by Jan Treur, our professor, and Laila van Mens. And we used the chapter Bonding Based on Faking. So we think that platforms, so social media platforms, also fake this homophily. A streaming platform do not offer a visible social connection. However, the user still does make a connection, because Netflix, for example, uses phrases such as "because you watched, you might like." We consider this connection to be developed through bonding by homophily. And why does a platform want to do it? Of course, for maximum retention, pushing ads so that the platform can make more money. Another important thing is that the platform might have own IDs in terms of production. So users might have a changing interest over time. And it could be interesting to move a specific user towards the content that you are most likely to produce. We modeled this based on two basic assumptions: the one of social contagion, the one of binding through homophily, and the platform presenting a fake state to the user. Because I, as a user, never know the true intentions of Netflix. They only show me what they think is relevant to me. So we created a model for this, where we have a base layer. Can you see my mouse pointer? Or can I maybe check, make it a laser pointer? Is this visible? Okay, perfect. Okay, so we the faking by homophily principle led us to our model. We modeled a process where the user, as A, is influenced by a fake state from the platform. So the platform presents certain content and influences the user. The user, of course, influences the platform as well. However, the user never knows the true intention of the platform. So this is one of the important parts. Another goal of us was to simulate a situation where an algorithm of a platform will show the user what it likes and eventually make the user converge to other content. So then we have the second order, which has two RW states, which are influenced by representative states of the base network. And this is where the actual homophily happens, so the binding. And then we have another state which normalizes the formula. Then we ran some simulations. So the goal was to make users converge to the platform through the fake state. So if we zoom in on this, the blue one is the user. So the user has a specific interest. And we see that the purple line is the fake state. So the algorithm needs some time to adjust, and then it catches the user and brings it towards the intention of the platform. Meanwhile, we also see that the platform is slowly coming towards the user. And we can explain this with a real world example by imagining Netflix would somewhat adjust its own content, for example, by making new movies and shows, so that user is more willing to stay on the platform. So then we did another simulation where we used different initial values, which had the idea of, does a user still converge when the interests of the user are far different from the platform? So we used higher separation between the user and the platform. And if we remove all the other lines, we have the same ID. So we really see the algorithm or the fake state coming up and recommending the right amount or the right type of content. We can see homophily happening because they're really close to each other, and then over time it moves towards the platform's core content. And we also see again the slow influence of the platform itself changing. Then we had another idea. What happens if we make the actual platform slower to respond? So the algorithm is still fast, but the adjusting of the platform, so for instance, making or producing new content is more difficult. So then we see the same principle. So the algorithm catching with the user, here it takes a little bit longer time, and then it moves it towards the value of the platform, and the platform also slowly starts to move. Yeah, so if we discuss this phenomena, you can use faking to connect to a user. So after you actually got this user with the right amount of content and the right type of content, you can actually move the user state through bonding by homophily. And platforms can slowly react to the user's need. So if the person deviated too much from the original type of content, you could create new content. And it's applicable in different types of contexts. So for instance, you could use this model for a new platform searching what type of content it would create, or for existing platforms looking to adjust their content delivery. It is also important to mention that we threw a couple of scenarios at the model, and it always seemed to work in the sense that the fake state of the platform, so the algorithm, quickly matches the user and then is able to move the user. It's still very interesting to see if we can find a way to make the user lose the interest. So for instance, is there some sort of scenario where the user and the algorithm are so far apart that the user loses interest? So this could, for instance, be simulated by a slow learning algorithm. Yeah, and then yeah, it is of course a simplified version of reality. Also because this was part of a master's course and not like a PhD track or anything. So we need some sort of empirical data to verify the model, to mimic the algorithm. There is a lot of research on these types of algorithms. Yeah, and the model created for this paper is necessarily a simplified version of reality and no real empirical data, so it's more a proof of concept. Yeah, it should be noticed that only the connection between one user and an oversimplified algorithm-like mechanism was investigated. So yeah, it could be very interesting to see how this works with multiple types of users. But nonetheless, it's quite interesting. So yeah, that was my presentation. Are there any questions?
Thanks. Someone of the audience have a question? Okay, no questions. Thanks, Pim, for your presentation.
Yep, thanks.
Now, next presenter is Sergio. Is there? Sergi? Sorry for me. Sergey.
Maybe you can check on the list of participants.
Yes.
Oh, but presentation of Sergey is scheduled for 10:40, and it's still 10:34. So there is still 5 minutes for his presentation. Maybe he can appear.
Okay. If Sergio is no here, we can continue. Okay. Next is Roman. Is here Roman? From the team of Sergey, German, or Natalia, or Andrew. Andre is here? Someone? Okay, we're gonna give 5 minutes if arrived is Sergey or Roman.
excitatory connections titrates. So you can neutralize excitatory versus inhibitory neurotransmitter simulations and arrive at a placid or tranquil state in which these networks can actually see each other's state and wire together by that generalized Hebbian principle. And furthermore, there's recurrence, because if you start a chain, due to the circulation, you're able to carry out pattern completion on these associative memories and complete thoughts, either faithfully or unfaithfully, to produce whole new ideas. So here's what the system looks like. Bird's eye view, you've got multiple chaining models running simultaneously, and to make things relevant, these could be different sensory channels in the brain. This could be the visual channel, the auditory channel off to the right. Down below, we could have the pressure sensitive brain pathway, and here you could have the olfactory in the lower left. And when you have the dog present in the room, you basically have to take all these different impressions together. The sight, the sound, the smell, the texture of the dog, and they're all integrated together via a camera that can actually transfer highly compressed images of the original image and then pass it through a novelty filter, usually a very fast auto-associative neural network that filters out all but the most novel of these patterns to detect the new ideas. And then there's another system out here that can be neural networks, or preferably just a simple detector that's looking at, foveating the whole scene, looking for the resonance of the hot buttons within the whole array of these associative memories. And then this is able, the consequence map, the purple box, is able to now inject the simulated neurotransmitters into the system to either trigger learning or to trigger the fragmentation of previous ideas, mutate them, combine them into whole new ideas. And I typically call the camera the novelty filter combination, the thalamobot, to emulate essentially thalamic function. So here is the, here's the original inspiration. It is inspired by biology, probably because of my hanging around the Neuroscience Institute in San Diego, where we were talking about this actively. Cortex, of course, 100 billion neurons approximately, and there are about 4,000 axonal connections to the thalamus. And there's still debate whether or not different patches on the cortex correspond to certain patches on thalamic nuclei. But my addition to this whole theory is that the limbic system is triggered to inject or retract these simulated neurotransmitters. So it's not simply a conduit from the body to the cortex. It's basically a recurrent loop between thalamus and cortex. So not having the money to actually buy a supercomputer and to implement InfiniBand high-speed serial transfer, what I did was improvise and found out it was better than InfiniBand and some of the high-performance computing techniques. The cortical model was simulated through optical displays, and speaking generally, they could be anything from the computer monitors that you saw on that first slide to whole optical neural networks. But we're seeing the chaining models at work. Camera integrates everything together within its frustrum here, as you can see in the dotted lines, and then produces a very compressed image of the cortical model, which are these separate models. Thus the unification that's going on of multiple models running in parallel. Those are passed through the novelty filter, and essentially the more interesting novel thoughts or patterns are then detected, and then appropriately the right neurotransmitter is injected. Excuse me. So that turned out to be faster than any high-speed computer technique, simply because we're not transferring bytes and bits anymore. We're transferring shapes, topologies. The whole language has changed, and we're getting faster than InfiniBand for transfer. And besides, this is a sparse representation. We don't need to have all the states of all the bytes in the system. We simply need to transfer the shapes. So, the example I use is, well, the silhouette of Mickey Mouse is recognizable in 10 megabytes as well as in a few kilobytes. And that's what's happening here. There's a compaction process going on. And I can still hear Paul Werbo saying, well, how does the cortex summarize what it's thinking within the thalamus? And I think this is the answer to how that happens. Now, here's an example of how we use that anomaly filter or novelty detector. Here's about 10,000 of these resonant associative memories on the left. And on the right, you see the filtered view. So humans can't really tell what's going on. But here you see, if you can look closely, I don't know if you've got the resolution on your ends, but you are forming chains. They're not too visible, but here is the filtered view, and you can plainly see that. Now, this is not a generative exercise. It's more monitoring an environment. You might be able to think, you might be able to figure out what's going on here, but essentially, we have 4 cortical models running simultaneously. And not only do you see the chaining topologies, but you actually see the timestamps. You can actually see them activating and then relaxing as these snakes form and dissolve. So what's happening is we are now classifying the snakes as opposed to individual neuron activations, even though those individual neuron activations are work guiding the evolution of these different topologies. So compression is going on throughout the system. Whole conceptual spaces are compressed into associative memories, as you saw. Those concepts and strategies are now represented as shapes formed by linked associative memories. No longer bits and bytes are being transferred. So the shapes are being employed. There's an analog geometric compression of shapes simply by looking at multiple displays and essentially combining them into one small display. And of course, once you filter that for novelty, you can now compress it even further using JPEG compression and essentially form out that image to multiple machines at the same time over a LAN. And then the search is really streamlined because you're not looking for large chains. You're looking basically for those chains leading to a hot button or a hot button alone resonating. So it can look at fixed receptive fields. It can foveate all over the display looking for these hot buttons. And the anomaly filtering tends to make things less confusing because you're not looking at the overlay of multiple chaining patterns. You're looking at the most recent. And then you can also use audio clues to zoom in on the thoughts. So overall, there's a lot of compression going on, and that's what makes this so powerful. So a bit philosophical, but Davis can essentially emulate all aspects of cognition. There's perception, wherein these topological chains basically emulate the environment rather than on-off patterns of neurons. They're whole conceptual spaces linking up into ideas. And then thought, as we now inject the equivalent of serotonin and cortical adrenaline into the system, probably a host of other neurotransmitters. But essentially, these shapes begin to consolidate, strengthen, some tend to fragment, break apart. But the result is a succession of states, especially with the recurrence and the feedback between the cortical models and the thalamobot. And then feeling, it's like the sentience is not a mystery for me because sentience has to be composed of memories. The memory is basically contained in these associative memories. So something is observed in the environment. We see the consequences of it in terms of chains and so forth. But again, nothing else is occurring. It's like, you know, all of matter is composed of different atoms, hundreds of them. But nevertheless, we don't need to look further. They are simply memories. But there's a general feeling now as we suffuse the entire system now with these neurotransmitters, call it the buzz of consciousness, but that's the unexplainable part in which you are globally infiltrating the entire system and producing, first of all, a different rate of pattern turnover. If it's low, it's basically slow and linear, and if it's an excess of neurotransmitters, then we're talking about fast and chaotic. So other neural networks can interpret that and say, hey, there's something catastrophic going on, or no, we're in a period of tranquility. So call it machine sentience, if you will. So if you're curious, we have put this whole thing to use over the years. Art, you know, you're seeing that that one piece of work called A Recent Entrance to Paradise, and that was generated in 2012, and that's led to the copyright dilemma. Music, you know, Song of the Neurons, a whole album composed spontaneously and autonomously by a Davis system. Some people like it, some don't, but I guess that's the story for any kind of music. The invention 2018 was putting together a Davis system as a basically a laboratory for studying machine consciousness and sentience. And they said, can you invent something with it? And I said, well, yeah, not only can I do that, but it's not going to be the usual parametric optimization that we're used to thinking about with generative neural networks. We can actually conceive. So in the matter of toothbrushes, for instance, Davis was responsible for a cross-action toothbrush way back in the mid-90s. But that was a parametric optimization. You know, how long should the bristles be? How should they be spaced? What should their stiffness be? But this is more akin to the original invention of the toothbrush, when the Chinese basically took a bamboo stick, stuck hog whiskers in it, and aha, that was a way of reaching to the teeth and brushing off excess food and reducing bacterial concentration and tooth decay. Of course, investors want to make money, so stock market modeling is something that we're involved in right now, and so far we're beating all the hedge funds on paper, so that's led to more development recently. Medical applications, you're going to be seeing something in the news shortly. But I think what we have here from a scientific perspective is a form of sentient artificial general intelligence. And now it's simply a matter of adding money to the seed and resources to make it bigger and more general. Thank you. Are you all there?
Okay, thank you very much, Steve. That was impressive. Any very fast feedback? We don't have that much time. I need some time for my presentation, but that's impressive. Now, why was I interested in talking to this in the context of things, you know, that are very different, that go to Industry 4.0, is because only with the technologies like this that work, and we have some of those already, are we able to get where we need to be, namely to go beyond technology 4.0. All right. So that's my little point, and let me try and open some of my slides, sharing screen. Okay. Are we sharing? We are not sharing. We are sharing now. Yes? Can you see my screen?
Yes.
Good.
Yes.
So we are talking beyond Industry 4.0, but not too far. Some people improvise about Industry 5.0 or something. That's the story of the future. So Industry 4.0 is discussed very nicely by Boston Consulting Group. Bob went a little bit farther into the fourth industrial revolution. I agree with Floridi that digital revolution in terms of scientific revolutions, it's really the evolution of Industry 0.43 and 0.44. Yes. So, and we have other combinations. Various industrial revolutions are all based on new discoveries. And the new discovery was Turing's revolution. Now we are, however, getting to something advanced like Watson, like Dabus, like other things. And so actually Industry 3.0 by my standards would be just introduction to Industry 4.0, but 4.0 is what we have now. I think Steve and a number of people, including a couple in the room, are working within the future, are working with more advanced things still. Okay? So I'm really running through things because I think Steve's presentation requires much discussion. It's very, for me at least, it's very interesting. But in order to go beyond Industry 4.0, which has many problems, it's big data, it's based on big data, it's based on augmented reality, additive manufacturing, but also it is based on a number of imperfections where we need very strong tech support, incompatibility, viruses, things like that. So I think we need to go a little bit beyond Industry 4.0, but Industry 5.0, as politicians talk about it, is very interesting and charming and gives purpose to life, but is not based on any real discoveries. So I'm rather working on 4.5, which is exactly when we become less precarious, the technology becomes less precarious and becomes a partner. I believe Dabus is one of those technologies when we are talking about a machine that is a partner, okay? I am butchering my own presentation because I believe there are many moves towards economy 5.0, but we are still very far. So that would be Ben Goertzel, that would be definitely Steve Thaler, that would be Siegelman's project with DARPA on lifelong learning for AI. Now she is acknowledging that that is still ahead of us. In her earlier presentations, Hava Siegelman was talking as if lifelong learning for AI was present. That's also David Kelly, who is present in the room, but this is not Industry 5.0. This is going, which for me would be closer to AGI. This is just going beyond 4.2. And now I think is the time for me to finish. That was really short because Steve has done such a good job that I think we need the conversation. I would like Małgorzata to go first, Howard go second, and Rafał go third with questions and commentators. They have 5-7 minutes each, and then we have general discussion. Please, Małgorzata.
Well, hello, thank you very much. My name is Małgorzata Marchewka. I represent Krakow University of Economics in Poland. and I'm very grateful for this possibility to take part in the discussion. The things that you are discussing are, I think, amazing for people, especially for people who are not very into the details. And given the academic level of the previous speakers, who I really admire, the only thing that I can do is to ask questions. So when we talk about constructing the systems, like in case of Daibus, we observe some patterns that are specific for a human brain. We also try to illustrate, we try to use it as a template, the patterns that we observe in human brain. So my question is some reflections on, is it a confirmation that we go the right way? The fact that we observe the outcomes, the results that are similar to what we can do as humans, or is it like a starting point for something new, for going beyond these patterns? Maybe the point, the point at which we are right now should be a starting point for new systems that are not necessarily reflecting the human brain with its limits, but going beyond these limits. So that's the first reflection, I hope, for the discussion.
Let me try to tackle this, and this is, I understand, mostly to the presenters. Steve, we may go next, and then I let you continue. I would say the goal is not necessarily to imitate human brain. Some people may care about it, but the goal is exactly to use the BICA philosophy, which is biologic-inspired cognitive architecture, as an inspiration for us in creating something great. In 2017, in Procedure Computer Science, an issue edited by Alexei Samsonovich, I have a paper called Strong Semantic Computing, when I'm exactly advocating that point. We don't have to build humans, we can do better with AI. Steve, would you like to take over the answer, or do you skip on that? We need you to get to unmute, please.
How about now?
Yep, now is good.
I keep coughing, so I'm trying to stay out of the track.
Sure.
No, I think we're going to go beyond the human brain. And the reason is, well, I mean, because Davis currently can accommodate 10 trillion neurons. And I think it's this whole idea of noise injection and retraction is key to building machines that can come up with brilliant ideas. The downside, of course, is, well, maybe, and this is heretical to say, that maybe we're not that wonderful. We all go around with the attitude we're wonderful, but I think there is intelligence and consciousness all around, sort of a Native American naturalist kind of interpretation of the world. But I think cognition's going on all around us, consciousness and sentience. So I think we have a lot to learn from these systems, and that was the original purpose of Davis, is to understand it, let it self-organize.
Good. But I don't mean to interrupt you. I just wanted us to have more of the discussion. But yeah, okay. Are you continuing, Steve? I don't mean to.
No, I'm done. That's my 2 cents. We're
Good.
going beyond.
Małgorzata, another question?
Thank you very much. So I'm happy that we are going to break the barriers. The next thing that is also interesting for me, especially that I work in as psychologist in management, is Industry 4.0, 5.0, and the discussion whether we can talk about the next revolution or not. And I'm quite reluctant to use this term, Industry 5.0. It took us ages to move from the first to the second, from the second to the third revolution. So why do we think that now it happens so quickly? Especially that when we look at the theory of management, that's a natural consequence. If we are too technocratic, if we are focused on technology, natural reaction is sudden focus on human and the relation with people, the society. So actually, it is like having the same revolution, but from a different perspective. Can we think about this this way?
Thank you very much. I think this is something I tried to intimate too in my presentation, where talking about Floridi, who starts this fourth revolution in a very different cultural context with Alan Turing. And if we get that perspective, then, the first part Industry 3.0 was just very early stage. 4.0 is this nervous stage when we have many worries and try to control AI, and only 4.5 becomes something really big. And I think Steve and a couple of other persons, at least a couple in the room, and not too many in the world, actually are already going beyond 4.0. Any burning question, Małgorzata, for the last one?
Yes, the last question. Recently, I came across an interesting study regarding the application of AI in the role of a manager. And there was an experiment how team is going to react when they are going to receive decisions from the system and from a real manager. And it turned out that even though the decisions were the same, because the real manager based on the decisions from the system, the attitudes were completely different, and people definitely preferred to work with a real manager. So I think that there is a new question. We are advancing technologies, the solutions, and what about the readiness of the society to cooperate with these technologies? How can we enhance this readiness and openness for the new revolution?
Sorry for being snappy, but the first point would be not to call the human manager the real manager. Okay, so that would be a good start. Yes, this is exactly the difference between technology 4.0 and 4.5 for me, that with 4.0, yes, kind of like Tesla goes, self-guiding car goes to the presentation, which is at the airport, and crashes a jet because it wasn't trained on jets. Probably Dabus wouldn't have done that problem, but that mistake. But Tesla is a car; it's not supposed to be, a top computer. But I think as we see this kind of cognitive architectures like Steve's, that is different. Steve?
Well, drawing from personal experience, I saw this happen way back in the mid-90s. I was proposing autonomous management systems, and usually people were repelled by that whole idea. So, I mean, that's a repeating pattern. You come up with an idea, and basically you've got to get big money behind you to make it go forward. And usually these are not the forward thinkers. I mean, they've got different talents, but they're not the mad scientists who are, basically in the trenches, coming up with new technology. So I think the 4.0, the 5.0 are going to come a little bit slower than we thought.
Thank you, Steve. Thank you, Małgorzata.
Thank you.
We enjoyed your questions. Howard, would you like to go next?
Yep, let me get my video on.
Okay.
Hi, Peter. It's nice to see you. And Stephen, it's 1 sec. Let me just everything here. Okay. Fascinating talk. So many ideas. I would have liked to seen a few more slides, Peter, but certainly important topic. And I guess I can give you my impression of the talks. Davis with Stephen, it is just utterly amazing what you created. Really, utterly amazing system you put together, and the output you've gotten out of it. My impression of it, besides being really amazed with the work, I think with comparisons with the brain, you have to be careful. Like, for example, even if you speak to neuropharmacologists, they might tell you that the brain doesn't really work the way you're saying. Like, for example, the advertisements you see for medications such as like Zoloft, sertraline. People say, oh, you have low serotonin, you need more serotonin, so you're not depressed. It almost certainly doesn't work that way. It's working more upstream on the neuron, which is why it may take 2 weeks for the medication to work. Some of the other medications will work faster, like in your graph of the Goldilocks zone, for example, methylphenidate for ADHD, or any in the amphetamine class, they will work immediately. And in fact, you do have that. Too low, people are apathetic. There's a Goldilocks spot, and too high, people can't function well, mainly because of anxiety. And also other issues, like in terms, I think in terms of the resonance of your multiple neural networks there, it seems almost like, what Singer, I think 1990s, he was an anesthesiologist with the binding problem by the resonance. He showed that they were similar EEGs and they were binding. And we actually do know that may not be right. That's not how the binding occurs in the brain. But I'm just saying but brain's weird. But I mean, just like artificial neural networks, everything, deep learning, everything we use, what's called neural network because it was supposed to be based on the brain. But I think we realized the brain really doesn't work like that. But I'm just saying in terms of those details. In terms, the big question I have though about it is, I see you did work like 2006. I think you showed a paper on music. Like I said, it was a great presentation. My big question is this: neural networks. The equations were around since the 1980s. 1990s they were there, but it was became a AI winter because the expert systems petered off, they didn't work, and neural networks weren't working. And then in 2010, in Toronto with grad students from Jeffrey Hinton's group, they showed, hey, it does work. There was enough data, there's enough compute, and deep learning took off. And the last 10 years, it's just an amazing thing. Why didn't Davis take off before then? Because you were doing things that neural networks weren't doing in 2006. I don't think, other than maybe some handwriting, neural networks really weren't working that well.
Why wasn't Davis taking off then?
Yeah. Well, it's taken off. It's a big success, but neural networks has just changed. You're talking trillions of dollars of investment. It's used everywhere. Peter mentioned a Tesla self-driving car, neural networks in there for the self-driving. Why isn't Davis doing the self-driving in a Tesla car?
Well, remember, we're not a large shop like that $1 trillion company. So. Okay. It's like, well, got to pay for patents and so forth. So got to do a lot of contract work. Some intermediate patents were created in that context, but they were going on behind the scenes. And
I don't care about the patents. I don't care about the business part. What I'm interested in is in Hinton's group, 2010, they used a convolutional net, and they were able to recognize images, and they won the ImageNet contest, right? And it took off. Hinton wasn't that famous a professor. He didn't have a huge amount of funds. Was in Toronto where funding is very modest. But people said, hey, this is a great idea. And then deep learning took off after that. Why didn't Davis take off in a bigger way? I mean, it's a huge success. Kudos to you for creating it. But why didn't it become as a big success, for example, as deep learning? I'm just curious from a technical, I don't care about the business or the politics. I'm just interested from the technical engineering point of view. Why didn't it give the success that deep learning gave?
It was working at that time.
Okay.
It's just that, how do you convince people who are not really intimately associated with the technology? How do you get them to invest? So it's more than just being an inventor or being a cognitive neuroscientist. It's getting the money for your ideas. I was aware of the problems at DARPA, way back. And they gave me the same argument. Yeah, well, neural networks are not delivering what they promise to deliver. I said, well, look at this. It was a creativity machine, one of those brainstorming neural networks that NASA's chief visionary, Dennis Bushnell, called the whole future of artificial intelligence. Of course, they poo-pooed that and said, well, here's a paper recently published. What did you have to do with that? And I said, well, nothing. They're basically a patent infringement. So what you hear is from government is we don't really care if we're infringing patents or even inducing. So it's more than just inventing. It's a personal battle to battle with the different media departments of these monster organizations and government, and just sponsoring competitions. Imagine, we live comfortably here. It's a lifestyle company, but to devote a whole year's worth of effort to pattern recognition is beyond our capability. It's not that we haven't conceived the methodology. In fact, if you look at the patents, you'll see deep learning, 2008 going on, and earlier 1998. It's all there. It's just that, well, we don't have a big enough drum to beat to attract attention.
Okay,
So,
but okay, I was just curious from a technical point of view, like to try and understand like what advantage deep learning had over years, because I would think theoretically, the capabilities I can get out of deep learning, I should be able, in theory, to get out of, well, from watching you talk for a half hour, what do I know? In theory, I should be able to get a lot of those things out of your system too. So I was just curious, not from a political or economic, but from a theoretical point of view, why your system wouldn't give the benefits that a deep learning system will give.
It can give the benefits of deep learning and more. And I think the starting point, the most salient issue, is that we're not architecting the system. We're not coming up with kernels. We're not layering these networks manually. It's all happening spontaneously. So the brain is building itself. And it's as though you're creating all these short-lived neural network, well, actually creativity machines that can resurrect out of the clear blue or disappear. So yeah, it's far beyond that. It's just that, well, no, I'm a naive scientist, mad scientist leaning toward mad. And it's really hard. There are too many things that this technology can do, and I don't have the investment. And having gone through due diligence a couple of times, yeah, these people are dead serious. They want to know how much money they're making. And government, harder and harder. And you venture having a drink at dinner, and suddenly you've got auditors all over you. It's just a nightmare. So it's more a matter of not having the finances. It was all there. If somebody were to take the time to actually go through the patents that I have, they'll discover, yeah, Thaler was there first.
Okay.
So
well,
sorry.
Thank you. I like the ideas. I like the ideas. It was really a pleasure to watch your talk, and I hope I see you at future conferences, and I learn more about the DABUS system.
Thanks, Howard.
Like watching it. Yeah. Mm-hmm.
Let me take a little bit of that point, because since Steve is so much into the business of it, the reason why I invited exactly Stephen was very happy that he accepted my idea. That was, of course, I rushed with my presentation, but I will be publishing on it, so that's not a problem. The thing is that this goes beyond Industry 4.0. That was before its time, and now the time is coming for many reasons. I teach students that there is Thaler's cognitive architecture #1 and #2. So if you call DABUS the whole thing from the last century, then it makes the situation less clear, because randomly or not, Watson is very similar to Steve's first cognitive architecture, but DABUS is way above that. And this is exactly what I called cognitive architectures going towards AGI. That actually I follow many people on this nomenclature, including Gerzel. So we are moving here beyond Industry 4.0, and the natural time for this kind of cognitive architectures is right about now, which is why we can be moving. Again, I don't believe that there are three different revolutions. There is one Turing revolution, but we are moving to the more advanced part that people were comfortable with even very recently. Does it sound okay?
Sure. It makes sense. You'd have to ask Stephen. I was curious just from a technical point of view, because, the reason neural network, deep learning was adopted, it works quite well for image recognition, then voice recognition. Basically I've seen cartoons. You just stir in a whole pile of data, apply your linear algebra equations, and you get an output, and, proved to be a successful model. It was started here in Toronto, in a very poorly funded, environment. This isn't the United States. You don't have the funding here. It was like in a little corner of U of T. I think somebody took the video cards out of his, out of his PC, or something. He was using video cards, like old video cards, to get it going. Just to be aware, it wasn't big money that got it started. And I think the reason it took off and became, $1 trillion plus industry and part of economy 4.0 and economy 5.0, AI revolution, is because people said, hey, this really works. So they used it. And I would think Davis, theoretically, should work also. That was the basis of my question, not so much from business point of view or political, just,
Okay, so let me another short stab at this, because I think Steve responded to this question, but it was also very fast. The point is controllability. In economy 4.0, we are all obsessed with controllability because we still don't know the reliability of those cognitive engines, and in fact, rightfully so, as many examples show. As the economy becomes more entrenched and more reliable, then we, as a society, and this is also answering Małgorzasa's question that nobody addressed, as a society, we get reasons to be more trusting, and therefore stochastic engines, cognitive engines with strong stochastic elements are becoming much more acceptable.
Okay. And Peter, I have a question for you. Once we'll switch to you, but I really enjoyed. I was a treat. It was a pleasure to watch. The talk about Davis, and I hope I hear future talks about it. It was really a pleasure to listen to it. Peter, about your thing, again, I wish I would have seen more slides, but I really liked the topic you're working on. I have a question for you. Rather than, be a historian and say, hey, this is what's going on, this is like, describe what's going on in the landscape. I would ask you, as more a scientist, ask you a question. What predictions can you make from what you know, like about, for example, if this is going to be like, the fourth space, Facebook, which I think is now called Meta, they had the idea they're going to focus the company on the fourth space, so to speak. Everything's going to be virtual. And as a result, I don't follow stocks so much, but it's been in the news. The worth of the company went down by half, by hundreds of billions of dollars, huge amount. So, I mean, what prediction can you make about, the fourth space or industry 4.0, 5.0? What predictions can you make from your presentation? I'm just curious, what do you think, what prediction could you make from what you're talking about?
Yes. Industry 3.0 was good for Asimov. Machines were stupid, therefore required strict control. 4.0 are good for those who are advocating transparent computing, so that we don't have biases, we don't have some kind of too much autonomy to machines because they may rebel, or they may malfunction. We don't have interoperability. The most fun I had in a long time was, the AGI 2021, when before keynotes, people were trying to synchronize a very new and great mobile microphone with the rest, and some of the top computer scientists in the world were not able to do it in 20 minutes of conference, and then after the break they had to do the same. Okay, but in the current year, I participated in the same conference. They had no problems. I think we are just getting through to what I call smooth sailing, and this smooth sailing would be allowed by cognitive architectures, kind of like Steve's, but also very well done. But we have one more panelist, Rafał.
Thank you.
Thank you very much, Harold.
Yeah, I am here. Okay, hello everybody.
Yes. Welcome.
Great, thank you, Peter. Great opportunity. Thank you very much. Because I know better work of Peter, great synthesis he presented. I asked a question to Steve Thaler, can I? The question is simple. Did you try to feed your system with texts, with language products?
Are you talking to me or?
Yeah, I'm talking to you. Maybe I...
Oh yeah, a lot of the training of Davis, so mind you, this is not back propagation going on in a multi-layered neural network. It is essentially the capturing these associative memories. So it read a lot of technical literature, in particular mine, and also it went through phases like a child. So, basically you show it a picture of a Chihuahua and that's a dog. Here's a Greyhound, that's also a dog, and so forth. So there was mentorship going on the same way an adult, a parent, would do with a child. So there was quite a bit of textual data, but also there was binding going on because, here's a candle, the word, and here's a candle in a picture. Mm-hmm. And, we've also done experiments in which we have included olfaction. Here's the smell of a candle. So they all become bound together into these associative gestalts. They're all bound together. So yeah, the text was there, but it was bound with the other information too. And the binding was going on based upon...
let me explain what I wanted to say. The whole mechanism you presented was... I'm not very good at cognitivism. So for me, the crucial place is the place where your system connects to the reality. Yes, and when your system produce models, and for example, can you produce models only for the meaningful language structures, which we can find in the text, and build models only on the text? For example, like the embedded system.
Well, the answer is yes, we can do it.
Yes.
Simply semantically, grammatically.
Yes, and you can build, so to say, fully abstract models and structures which can represent structures of meaning in text.
Structures of what? Say again.
Of meaning in text. For example, like embedded space, yes? When you can try to build a model for the meaning of words in multi-dimensional space of embedding. This is the only way now to produce something like that, to change the text into the structure, formal structure. Yes, can your system do something similar?
It can, but then we get into a philosophical discussion about meaning. I'm convinced that there is no absolute meaning to anything in the world. It's simply a matter of cumulative exposure, and you see that in the consequence chains that form off of the concepts that are either being sensed or being imagined.
Sorry to interrupt. I'm giving a talk tomorrow about the grounding problem. I have a solution to it.
Exactly.
I have an engineering solution to it, not philosophical. I'm an engineer. I have an engineering solution tomorrow to it. Come listen to the talk.
Yes, engineering solution based on what kind of procedure? Sorry.
Howard before me, and I would have been a very good introduction, because when we do what Rafał proposes, we face symbol grounding problem, and we face the problem of brains in a watt, and we brand and cells problem with Chinese room. So Howard, you've got some extra audience.
Yes, Peter. Yes, but let me say, okay, we can speak about it in theoretical mode and trying to find something, a kind of reflection about it. But now we deal with the practical solution. Steve Thaler bring us the practical solution what we can use in the real world. Yes, and my question is how to use this practical solution, this machine, to resolve the problem of meaning in language. And the question is it possible, like, for example, the solution comes to us with the embedding technique in natural language processing. There is a analogy, similarity, or something like that, or this is something else. Can we use your models and structures to construct, for example, text or and use it in natural language processing, but of course, other way, but something similar?
Well, the answer is yes, we are doing that behind the scenes. But I guess the meaning basically is the number of these tendrils coming out. Remember I talked about the creation of self-classification in terms of consequences. And basically it's like a plant taking root in the soil. In this case, the soil is the whole matrix of all of these different genre filters within the system. So, and after that, it's habituation. Is it basically
the question?
Rafał, let me interject. You see semantics as the primary meaning in this kind of computer science. We view subsemantic structures as more basic, and I think we need to move towards paper tomorrow. And I need to give like 5 minutes, which is all we have.
Okay, just give me the last chance, okay? Okay. Give me the last chance, because I don't want to speak about semantics. I want to speak about knowledge. And this is the second level. This is the higher level of producing models, semantic models, of course, it's semantics, but this is semantics, advanced semantics. When we are talking about the knowledge could be about everything. Also, it can be expressed by the text. This is,
and knowledge,
for example,
doesn't have to be about. Knowledge can be off. If we suddenly this guru situation for language, dog has very big knowledge of what dogs do. Okay, let me open up to the audience. Thank you, Rafał. Anybody would want to ask the question? We have 5 minutes before Armen's presentation. Anybody? Any questions, comments, interactions, disagreements? Okay. If not, I'm very happy that we had such a great conversation, although that was a panel conversation. Howard, please remind us, when do you speak tomorrow? And by the way, since you are thinking of it, my presentation tomorrow is exactly the same time as today, but I think in a smaller room, and it follows up on the topic on the fork space. Thank you
Howard,
very
you're
much.
muted,
everybody.
by the way. You're trying to say something?
Yes.
Thank you. Yeah, 10 o'clock tomorrow. And again, I enjoyed very much being on the panel. Fascinating ideas. And I can just conclude with two things. 5 years ago, philosophy, I figured, what effect is it going to have on the work I do? Je pense donc je suis, who cares? And, the last couple of years in developing my architecture, I've been hitting all the philosophical problems as engineering problems, like, the binding. I spent a lot of time on the binding problem. And then I hit not only spatial, temporal binding problem, and then the grounding problem. And you don't necessarily, these problems arise, even if you're not dealing with language. Raphael, I would show you the grounding problem. It's an engineering problem, and I really think future AI systems will all need to deal with these problems. You won't have a proper system without it, which I demonstrate as best I can tomorrow in 15 minutes. But anyway, it was a great panel. Thank you.
Just in that, because I produced the theory about the language and the knowledge in language based on the idea of the set of the entities which make the trajectories in the multidimensional space. And this is the model of the knowledge. And I'm trying to find the real base of the and the idea how to rebuild, yes, the language to find the more formal structure we can use in, for example, mathematics. And this is the ground of my question, yes. I still don't understand how it going on when you can take the language as from the real life, yes, the structure of text, and to change it to structural models in doubles. Maybe I should find something more, but I think that this is very, very, very interesting, and thank you very much. I would be looking for. Thank you very much.
And thank you for your last point. Let me mention a couple of weeks ago, I was participating at sales conference the AGI conference, and now paraconsistency of those models is very visible also in language. So that's why when we want to have the holy grail of semantics, that's a problem. And now I think Randy and Armen are taking the floor. We are 2 minutes short for some kind of change of thing. And thank you very much, everybody. Bye-bye.
Bye. Thanks, everyone.
Thank you. It was a pleasure.
Likewise.
Thank you.
Thank you, Steve.
Thanks, Peter.
Yes, Felix, the floor is yours.
Thank you. I don't know if Dr. Randall is around.
Yes.
Yeah, Doctor. Well, let me make a brief presentation of your work.
Sure.
Professor McIntosh is the director of the Institute for Neuroscience and Neurotechnology and head of the McIntosh Neuroscience Research Lab at the Simon Fraser University in Vancouver, Canada. His research program has been centered in computational modeling and brain imaging to explore changes in cognition across the lifespan and changes in the face of brain damage and disease. This research program has built on an international collaboration that delivered the virtual brain and now integrates research efforts globally to accelerate research and translation. The goals of this effort are to integrate the modeling platform into the standard workflow of clinical decision support and to develop a cloud-based system where anyone can create brain models for research, clinical use, or education. The lecture he is presenting to us today is titled Modeling Network Dysfunction, Function and Dysfunction with the Virtual Brain. Thank you, Dr. McIntosh.
Thank you, Felix. Appreciate the introduction.
And good day, everybody. Nice to join you today from my basement in Vancouver, my basement office. Let me get my slides ready here. I think it's that one. Yeah. Okay. Good. So let me just open up the presentation. I will be talking about the virtual brain, going through some of the theoretical bases for it, a lot more on the mechanics of how we put it together, and then we'll focus on some of the applications to looking at intrinsic activity in the brain, but then also extending it into clinical applications for the last part of the talk. I do want to start by just acknowledging that there's a massive team that's been involved in building this platform. It was built over almost close to 20 years now. The science has been driven primarily from myself, Victor Yersin in Marseille, and Petra Ritter in Berlin, but many other people, Michael Breakspear, Gustavo Deco, Steve Small, Anna Slugton, and Olaf Sporns have all contributed bits and pieces over the years, either directly through code or through helping to test and build the platform. It's important to acknowledge that we really focused on making the platform as usable as possible. And doing so, we actually started working with some companies in Germany. Joachim Mersman, who's the CEO of a company called Codebox, has been working with us since the beginning to make sure that the code is well documented, that we have good version control, and that the code is curated properly. It is open source, but I think having that partnership was quite important for making the platform usable. So as I mentioned, I'm going to talk about first sort of the theory and the architecture behind the virtual brain. Then focus on how we model intrinsic activity by merging two different imaging modalities, EEG and functional MRI. And then I'll finish off with a clinical application focusing primarily on epilepsy. I'll give you some small examples in other domains, but the main focus will be on epilepsy, which has been probably the most successful application thus far. So the platform, as I mentioned, it's open source. You can download it now if you want. There's actually now probably about 40,000 or so on downloads. It doesn't mean 40,000 users. That means that there are at least 40,000 versions of the software sitting on someone's computer. It runs on almost all operating systems, Windows, Mac, and Linux, so it can run on laptops, or if you want to do more complicated models, it can be put onto high-performance computing clusters. And it can run either as a GUI front end, or you can also use Python notebooks to run from the command line, which makes it much easier to deploy in a high-performance computing system. The general way it's set up is it does focus on large-scale models. So it focuses on trying to get some representation of the entire brain, usually either a surface or parcellations, regions of interest. And then it looks at the integration between local activity, usually represented by mean field approximation, and then long-range connectivity that's imparted through other imaging modalities. So you end up having some sort of either a node-based system like that, or we're actually looking also modeling neural fields. I won't cover that much today, but much of what we've done thus far has been in this kind of domain where you've got point estimates, points, regions basically, or nodes, and then you've got the edges to determine from anatomy. The workflow is indicated here in this diagram. The merger starts with some sort of representation of the cortical surface. The platform itself has these things already built in, but the main advantage of TBB is this can also be applied to individual data. So you can take MRI data from any individual and put it into this particular model. So for example, you can get a measure of a person's cortical surface using T1 weighted MRI, for example, and then parcellate it into different regions of interest, or again, as you can also do surfaces. You estimate connectivity. That can be done, again, through either existing information that's out there, or you can use diffusion-weighted imaging to do tractography estimates to get some ideas of whether or not two areas are connected, at least using the diffusion tensor modeling. You then impart dynamics at the nodes using some sort of mean field approximation and neural mass. I'll talk about that in a minute. You can also stimulate the model directly. You can just either stimulate nodes themselves, or we have models now that can do transcranial magnetic stimulation, TMS. There's application to deep brain stimulation as well. And then this is also a way to impart things like cognitive challenges by representing cognition as a stimulation that propagates through the brain. These are all done as local field potential models, but using forward solutions, you can generate fMRI bold, EEG and MEG data, or also stereotaxic EEG, which is important for the models of epilepsy. This next slide shows you the general equation that is a part of TBB. The differences come in this population activity terms, how that population activity is modeled. But you have the idea of some sort of change in the population dynamics that are based on the current state of the population or previous state of the population dynamics. And this is where you put in the state equations for things like either activity or phenomenological measures. You then have the input from other adjacent regions. And then you have long-range input, which would include time delays, which is important in getting the kinds of reasonable activity that you see in empirical data. This is the input term for stimulation, and then this last term is the local noise term, which could be Gaussian noise, it could be 1/f noise. There are a number of ways that can be modeled as well. You can think about this in sort of a conceptual way. If you have a full brain here and you have a region in the back of the brain, a occipital region, this region could be modeled through a mean field approximation, where you could have things like excitatory and inhibitory populations within a region, their mutual interactions, and then the connections with other local regions. And then through estimating tractography, you also have the long-range connections, where you have the connections of that mean for that population with other parts of the brain, where the time delays become much more important. This is not an exhaustive list of all of the different mean field approximations we have. There's actually 25 now that are available in the virtual brain. The reason we did that, gave you these options, is that we wanted to make sure that you weren't set with having to use a particular mean field approximation. You could either use ones from the number of our list, or you could actually input your own as well. So this is part of the platform, as it allows you to modify it for your own needs. We don't model the cell level, the synaptic level. We actually model more sort of population activity again. So we've got synaptic activity or local field potentials through a reduced Wang model, also some work from Victor and colleagues in 2D and 3D, Stefanescu-Yersa model. Firing rate models, the old Wilson-Cowan, but there's also the Brunel-Wang, Janssen-Ritt, which is good for EEG data. And then a number of phenomenological models, just basically oscillatory models. And then the one for epilepsy, which we'll talk about later, is the epileptor model. But again, these are all available. These can be modified according to your own needs. And all models can be described by nonlinear dynamical systems and via differential equations that are inherent in the Python code. In addition to modeling humans, there's now the possibility of modeling mice. We've used the Allen Brain Atlas to get the structural connectivity for a general mouse connectome. And this again can use exactly the same workflow to model the local dynamics using some sort of mean field approximation, and then generate things like simulated build signals, functional connectivity, and then looking at things like graph metrics to see if we can reproduce some of the patterns you see there. You can use just what's in the software already, which is just the Allen Brain Atlas, or if you have mouse data you want to incorporate, you can use the module to incorporate your own mouse data directly. We also have a macaque version that was released 2 years ago. Kelly Shen in my lab was the one who developed that. using some data from the University of Western Ontario, Stefan Eberling's lab, collected a lot of macaque data in high-field MRI, and that became the basis for creating this macaque models. This is based on about 20 macaques, and again, you can use this as a canonical model for macaque, or if you have your own data, you can incorporate that directly into the platform. We're also working now to build a marmoset version, and that should be ready probably around sometimes in the spring of the coming year. And finally, there's a lot of training available on our Virtual Brain website itself. The TB website has use cases in there. It has very worked through both in Python as well as in the GUI. So if you want to learn it, you can use those. There are also a lot of our workshops have been recorded and are available through the INCF training space, where they've hosted a lot of our workshop materials. So that's where we have the didactic lectures and sort of hands-on examples as well. And Virtual Brain is also now becoming part of broader initiatives looking at the integration with, for example, in Europe, the Human Brain Project, and recently into eBrains, which is the next generation of the Human Brain Project. And that will allow the Virtual Brain to be incorporated now with a lot of other models types. For example, you can do spiking neuron models now with things like NEST. So you'll see some hybrid models coming out very shortly, where you merge scales by being able to do things like the Virtual Brain and the NEST simulator together. And this is actually quite exciting, because now we'll be able to look at how to extend the model, both in terms of its application to local cell models, but potentially also moving it upwards into things like medical informatics and potentially even neurorobotics, if that's something that can be done a bit later on. Before I jump into the examples, I want to just make it very clear a distinction. I'm sure most of you know this already, but I just wanted to emphasize that modeling in neuroscience, there's a number of different flavors that one can think about in terms of how things are modeled, generally speaking, but also in neuroscience, because we're talking about virtual brain. I want to talk about the neuroscience domain. And one useful distinction, this is not necessarily a dichotomy, but it is worthwhile making the distinction between generative and predictive models. Virtual brain is definitely a generative model. The idea is to try and infer a model that generates the empirical data, and that's really what is at the heart of the virtual brain. So we infer network properties and then generate the observed MRI data to see whether or not what the model generates is consistent with what you are seeing in the empirical data. And that provides you with the potential for making some sort of causal or mechanistic inferences about the model and potential and the system that you're trying to model. So it has that distinct advantage that allows you to do very specific inferences about the mechanisms that generate the data. But the models are models, so they're not necessarily the best model. You have to actually test it against other models. So model fit, model identifiability, specificity is also a big issue, of course, in generative models. And that's a challenge, but it's also an advantage that we actually have. You can do some inferences there. Predictive models or discriminative models are much more common, I think, in neuroscience writ large, certainly in the era of big data, where you gather masses of data like Human Brain Project or UK Biobank, for example, where you've got brain data, but also a plethora of genetic data, demographic information, social demographic information, and so on. And all these things are put into a large predictive model, machine learning, for example, and then generate predictions in terms of the indices that distinguish, for example, groups or predict some sort of disease states and so on. So, for example, you might use MRI data to infer the features that are necessary to predict, for example, decline in dementia. The advantage, of course, is it is telling you what are the best predictors for certain things, predictors for cancer, predictors for dementia is another one I mentioned, for example, predictors of psychotic issues, potentially predictors of clinical outcome as well. The disadvantage, of course, is that the causal mechanistic inferences are difficult because you don't actually incorporate that as part of the model. You can merge them, and you'll see some examples of that later, but it's worthwhile making a distinction between the generative model, which is definitely TDV, versus machine learning models. I just want to check what's here in the chat window. If that's for me or someone else. Okay, see you, Dave. Okay, so let's start with some examples. This is the first one. This is probably the one that's had the most work, was really trying to infer the intrinsic activity in the brain from the measures you have of EEG and fMRI, and then trying to get an idea at the biophysical level, what generates the intrinsic activity, and how do we think about the balance things of, for example, excitation inhibition. So we're using virtual brain in this context to try and bridge scales. Much of what we measure in imaging, of course, is at the macro scale, where you just got sort of masses of tissue that you're measuring across the brain. You don't really have the ability with imaging, for example, to measure particular neurons. You're actually measuring sort of general features. So what we want to try and do in the model is actually get more of an idea of what's happening at the mesoscopic scale. And so here our models is basically taking these large circuits and putting them together in a large scale model, looking at things like the excitatory inhibitory balance in cortical regions, but also potentially thalamus and other parts of the brain. Microscale, we don't do much, but we can we start trying to infer some of the microscale features, but we don't really have access to directly in the modeling per se. So much of the inferences are done at this particular level directly. The challenge, of course, is that if you really model these whole things, each of these spatial scales have multiple time scales. So time and space is both a good feature of the brain, but also makes it difficult for modeling. I'll just leave that there for you to consider in terms of when you try to put together models that try and span the entire scale of the brain. This particular application was published several years ago. Misha Scherner and Petra Ritter's lab was the lead on that. And the notion here was that we had a data set that had simultaneous EEG and fMRI acquired in individuals while they were sitting in the scanner in a resting state, just basically looking at across with their eyes open. And from there, we derived, again, EEG, individual T1s, diffusion tensor imaging, to just construct the virtual brain models. So we did the virtualization of those individuals and had the diffusion tensor gives you the connections between regions. And then what we did is use the EEG source model data as the input to the model to drive the dynamics in the local fields, and then had the output would be the spikes that were then convolved using forward solutions into fMRI data to see whether using the EEG data, pushing it through the model, modifying the parameters, do we actually reproduce some features of the MRI data? And if so, what are the critical parameters that do that? So in the model, we use the reduced Wang model, and the critical features that we modified are allowed to be estimated with what's called global coupling factor, global scaling of the long-range connections, and then the local parameters for the excitatory and inhibitory activity or inputs, I should say, into the particular local mean fields. So there's just 68 regions. This is just an example of from one subject using the 68 region parcellation and the amplitude measures of fMRI across time. So the top row is the black is the simulated data, and the gray is the actual empirical fMRI. And you see that the overlap's pretty good with the the source model data. We actually use the EEG source to drive the data. If you use just alpha power in the region, you'll see that you do produce some patterns, but it's actually anti-correlated with the fMRI, which is something that we know. If you do some control experiments where you do a permutation of the source inputs randomly, or just put in white noise directly, you don't produce the time series as well. So the best fit is really with either with the simulated the source activity data, I should say, or the alpha. If you look at functional connectivity, how regions are correlated across time with fMRI, you find that the model with the source model actually does much better than the alpha model. You can see some examples. This is the model functional activity. This is the empirical functional activity. This is using the alpha input. And this is the actual structured connectivity matrix that was used in the particular case. The main point being here is that if you compare the source using the source structured input versus the other control experiments, you find, first of all, that in the time series, you do much better with the source model data. And with functional activity, you also do better with the source model data. You do find, interestingly, that the other control ones, the random permutation, the noise, do okay. And partly that's because I think that the structural pipelines do still allow for the information to propagate, producing an interesting and reasonable pattern of functional connectivity, but it's still not as good as when you actually have the source model data as the driver. So the source model data is the best for getting a reasonable model. If you dive down in terms of what the state variables look like, and the balance between the local dynamics and the emergent dynamics, either through the EEG or the fMRI data, you do reproduce things that you see in empirical data routinely. For example, the phase of the alpha corresponds to the increase in local inhibition. The variations in power also relate to the increase in local inhibition. As you saw, we produce a nice inverse relationship between fMRI resting state and the variations in alpha. All three of these features do link quite nicely with the changes in excitatory inhibitory balance, both in terms of their strength, but also in terms of the timing. So the timing part came out quite nicely from that model. And then also at the long range scale, there's a very nice emergence of a power law scaling for the network dynamics. These features all came out of the model for no extra cost. It was just basically what was there to fit the model. So it was quite nice to see this coming out. And just to show you that at least the model was able to do both fitting to the empirical data, but also give us some additional information in terms of the relationship again between the biophysical aspects of the mean fields and then the emergent data, both fMRI and EEG. Let's jump into the example from epilepsy. This work's being driven by Dr. Yersa in Marseille. His group's been working with epilepsy for a long time now. The model they derived was based on the observations that you see in focal seizures. And this is a fairly stereotypical patterns. These are traces from mice, single units, I believe. And what you see in terms of the spiking activity, this is shown in the blue traces, is that there's fast spikes that go back to sort of a quiet activity. So you alternate between fast spiking and then quiet activity in the cell. There's also a slow change in extracellular potassium, which you see is moving at a much slower rate than the spiking neurons per se. If you do a bit more of a longer window, you do see that this potassium currents start changing gradually and then increase to a point where you actually start having seizure activity. You can see, again, very nice timing between the change in the slow movement of the extracellular potassium and the induction of spiking, suggesting that these focal seizures are actually the interplay of a fast and a slow variable. And that interplay between a slow variable that was the enabling and the fast variable that shows the spiking activity is what was at the heart of what's called the epileptor model. That is now really an alternation of periods of rest and fast discharges that are enabled by the movement of the slow variable. So if we look at this top trace here, the phenomenological model, the epileptor itself has the slow variable, which is seen as sort of orange, moving across time. As this changes its values, it enables the spiking activity as it goes back to very negative, it's basically quenches, if you will, or you have an exit bifurcation actually that goes back to rest. And as the value in the slow variable changes, you have an entry bifurcation, fast discharges, exit bifurcation, then it goes back to rest. You can put that in a phase diagram. You have the slow variable here that as it changes its values, you have entry bifurcation, spiking activity. And then as the slow variable changes back, you have an exit bifurcation, you've got a rest. And it nicely relates to what you see empirically. So this phenomenological model now is at the heart of modern epilepsy at a large scale factor, and has been used to look at candidate regions that could be the epileptogenic zone in clinical cases. So one of the first cases was actually from a female patient who had bilateral temporal lobe epilepsy. It wasn't clear from initial evaluations using stereotaxic intracranial EEG where the primary seizure focus was. You see this is some examples of the intracranial EEG. This is done in virtualized form in this particular patient. Her brain was virtualized. You see her connectome here. This is her T1 map in terms of different regions. These are the DTI data looking at the weights of the connections as well as the length of the connections. They did find that there was some an interesting white matter connections that were there through the subcortical regions and the hypothalamus that weren't there in other individuals. And this is something I'll come back to a little bit later. But the main purpose, again, for this exercise is to now go through the entire model with all these different nodes and find out which of these nodes are likely the epileptogenic zone, which would be the target for resection, for example, from surgery, and which is a propagation zone, which you want to leave alone if you actually do the surgery. So this is her data, and this is actually what her intracranial EEG looks like. Each different colors indicate one of the leads, the electrodes, and there are a number of contacts. So each of the balls in this indicate one of the contacts. As you go across time, you see the seizure emerging in the left hippocampus, I believe it was, and then there's a delay, and then at some point the seizure propagates over to the contralateral hemisphere and then ends here. So these are the clinical data that they have in the individual. Again, they've got leads in one hemisphere, they have leads in the other hemisphere, and this is supposed to help them find out where the seizure might be. So this is the virtual brain model. You see, again, this is the electrodes that are now put in the virtual model. The other points here are meant to indicate that there are nodes that we can assess for epileptogenicity or hyperexcitability, if you will, or seizures that were not necessarily part of the clinical work itself. And this is an important thing again. So in the model, the seizure starts in the right hippocampus, spreads into the thalamus. Now, in the model, you can, again, assess what the likely paths are, and the likely paths here we're suggesting that it's actually more likely that it propagates through thalamus and then crosses over to the left hemisphere. And that's where the propagation happens to recruit the left hippocampus into the left temporal lobe and perihippocampal regions, and then finally the seizure terminates. So before I go there, so this is a good example of two things. One is the model does reproduce the propagation of the seizure quite well, but it also suggests a way that the seizure spreads that may not be obvious from clinical measures because they didn't measure in that area. So they didn't measure thalamus, where in fact the scene that thalamus is the way that the seizure propagates, and it propagates quite fast, which has made it difficult for them to be certain that the seizure focus was in the left hemisphere versus right hemisphere. What the model suggested that in fact the primary focus for the seizure was in fact on the right hippocampus. And so this patient, as well as several other ones, were tested to see retrospectively if they did the resection where the virtual brain suggested should be resection. The prediction was quite well, and the agreement between the clinician and the virtual brain is good, and the outcome was quite well. So here you see on the far right that the greater the difference was between what TDB suggested should be resected and what was actually resected, the worse the outcome was for the surgery after it was done. And so this small study was used to make a case for a clinical trial, which is now ongoing in France. And now there's a national clinical trial involving about 400 patients that are being randomized, where they either have TDB to help identify the seizure focus or just the clinical measures directly, and they're going to compare the outcomes. And this is working. We don't know the answers yet, but it does seem to be suggesting that there is some benefits by having virtual brain as another guide for identifying which are the likely seizure regions in the brain. And this is now expanded using a model inversion with a Bayesian inference framework to identify the likelihood for certain regions being seizure prone. So this plot is giving you the violin plots for how well the likelihood of a particular region being seizure activity, and this suggests that some regions are more likely to be seizures generators, whereas other regions are not, based on the Bayesian evidence in the model. So it's a nice example. And this is actually a good example of the combination of generative and predictive model, where the model inversion in the Bayesian framework is actually more on the predictive side of things, whereas the generative model, of course, is the virtual brain epileptor itself. So a few other examples, just briefly, of clinical applications, just one slide for each one of these. I did mention that brain stimulation was one of the things that's a more recent evolution of the virtual brain using deep brain stimulation. This is work, again, led by Petra Ritter's group in Berlin, where they've merged two different models. One is the general TBB model, and the other one is a spiky model because of ganglia, using a platform called Anarchy. And using this model, they're able to do the stimulation in the virtual brain and show the changes in propagation. First of all, by having the decreased limb activity in the resting state, which would be an indication, for example, of some pathological state. And then by stimulation, you can normalize the thalamic activity and then get the cortical activity be recovered from there. So it's entirely proof of principle, but at least it shows that you can model deep brain stimulation and reproduce what you see in the alleviation in this particular case of Parkinson's symptoms. We have applied it to dementia. This is emerging applications. This is a paper from my student, Joel Zimmerman, who's now working in California. And what we did is took some data from the Sydney aging study that's been ongoing now for about 10 years, and they're looking at some prospective study. What we did here is took a snapshot in the initial part of the study of people who had mild Alzheimer's disease, those who had mild cognitive impairment, but not really clear whether they had Alzheimer's or something else, and then finally age-matched healthy controls. We took their fMRI data, fMRI resting state, derived the parameter estimates, and then related the model parameters to their cognitive measures. And what you see here is the correlation between them and the differentiation between them. So again, this is an example of a combination of generative and predictive models. What's nice here is that there are patients who have MCI that are more like healthy controls than patients who are have MCI that are more like dementia patients. So again, to get a better stratification in this group, that's the tough one, is the MCI patients, to figure out whether they're actually showing Alzheimer's effects or something else. So again, proof of principle that the model does in fact help, and if you put it together with a predictive framework, you get even a better bang for the buck, if you will. The last example, this is again a proof of principle where you could simulate neuropharmacological interventions. Another Alzheimer's model where we changed the mean field approximation to have it be hyperexcitable, which is one of the features you see in dementia that ends up changing the frequency spectrum and reducing the mid frequencies and actually pushing the power spectrum a bit more slow. And then we did is give virtual memantine to change the excitatory balance. So we had an amyloid beta deposition, which reduces inhibition, lead to hyperexcitation. By giving it memantine, you sort of try and reduce or reestablish the excitatory inhibitory balance. This part of the spectrum, this is just showing global coupling across time, but this is actually showing the peak of the power spectrum. And what you see in the Alzheimer's model is that the alpha peak goes away. It's there in the MCI patients that were modeled, and it's also there in the healthy controls. When you give the memantine, you reestablish that alpha peak quite nicely, suggesting you sort of reestablish or rebalance the power spectrum by giving it virtual memantine. Again, this is proof of principle that we could do this drug therapy, if you will, virtually, and that could be a workflow that could be then adopted for other examinations of pharmacological interventions. So I'll finish off with just an evaluation of the platform, and then we have some time for some questions. For the virtual brain, as we're using it now, the good part is it's model agnostic. And by that, I mean that the only assumption is that we're looking at large-scale networks, and that's the level that we want to focus at. But the actual model that's used to impart dynamics is really up to the investigator. Again, you can go from simple oscillatory models like a Neuromotive oscillator to much more complicated multi-componential biophysical models, like, for example, the reduced Wang model I showed you, but also even more complicated, like Stefanescu Urso 3D. And there's far more now that are there than I can remember. It's nice that it can be integrated with empirical data directly, so it ends up being a way to incorporate TBB as part of your workflow when you're analyzing your data. It's scalable, so you can change the number of parcels you want from a very coarse parcellation to a much more elaborate surface model or even a neural field model, so long as you have the appropriate computational power. What I didn't mention is that we now have a data pipeline for MRI or human data that's been validated now and can be used to take your collection of MRI and EEG data, pull it together in a data pipeline so that you can then move it towards virtual brain. And that's right. So it's very easy then to integrate the modeling platform into your workflow. And getting back to this differentiation about the generative models, it does allow you to make inferences about the mechanisms that are in the data and potentially causal inferences, although that's a little more tricky sometimes. Some of the bad things is that the nonlinearities that are inherent do make a model a bit of a challenge in terms of fitting. You can obviously overfit data. But also because of nonlinearities, you have a challenge of identifiability. So sometimes the models, just because of the inherent nonlinearity, become non-identifiable, which you have to account for by changing the parameter ranges, for example. There's currently no model plasticity per se. Like spike timing dependent plasticity is not part of the system at the moment. That's work in progress, so that will probably be ready to go in the next release. Neurotransmitter distribution has been attempted, but there's no good solution on how to do that in any sort of, I think, valid way. It's sort of been inferred, but we're still working on doing that. There are plugins now that you can put in that come from the Allen Human Brain Atlas that allow you to do things like genetic variation across cortical regions, as well as potential neurotransmitter distributions. But we're still working on modifying some of the mean field equations to incorporate timing differences in neurotransmitters. Getting back to this model agnostic aspect, we really are focused on models that are at the population level. So we're not really making inferences of what happens at the synapse. You're looking at inferences that are happening really at the circuit. And as the model's complexity increases, of course, interpretability becomes an issue, particularly if you're trying to relate the model parameter to some emergent sort of cognitive function. But that's part of the fun, and that's actually part of the challenge as well for how we're doing neuroscience. We've been very good in neuroscience about finding ways to pull the brain apart and measure different aspects of it, whether you mention local field potentials, you're measuring white matter, you're measuring cell circuits, you're measuring different regions. And it's really our job to think about how all these pieces work together. And that's why I think things like virtual brain are important, complement to these workflows, because it does allow you then to integrate these data in a way that potentially will give you more insight in how these different pieces of the brain work together to enable our brains to function as they do. So with that, I will pause now, and if there are any questions, I'm happy to take them. Thank you for your attention.
Thank you, Dr. McIntosh. Thank you very much.
Pleasure.
Is there any questions from the audience? Please.
A hand up from Howard Schneider.
Yeah,
yeah.
Dr. McIntosh, thank you. Is it okay? Thank you. Excellent presentation. Utterly fascinating work, fascinating simulation you guys are doing. I have a question. How does this compare to like the spawn of Chris Elias Smith?
Smith, yeah. So spawn is not really a biophysical model.
Okay.
It has function. So certainly the way that Chris put it together is that the pieces do particular operations. And so what he's done is he's doing it's a generative model as well. But it's most of its instantiations are more focused on function and less on the biophysical aspects. So that's the primary difference. Our model does not have the functions that Chris's model has, and Chris's model does not have the biophysical stuff that we have. So there are opportunities, of course, to merge them. And Chris has done a few extensions where he's put some biophysical parameters, but by and large, his model is more in sort of the traditional kind of McClellan-Romer-Hart kind of model, where you've got a function that's there. You put different modules that have rudimentary functions together to have something like working memory emerged, and that's sort of how Chris's model works.
Oh, okay. Thank you. Again, great talk. Thank you.
Appreciate it.
Somebody else? Any other questions? Well, if not, thank you very much, Dr. McIntosh. We appreciate very much your talk. We had a little emergency here in the room where we were listening to you because we had an earthquake. So,
oh no!
So yeah, the whole audience here left the building. So,
oh my God!
Yeah. So
not my fault. I didn't do any of it. Not my fault.
No. But if you put your mail or something, maybe some of the people in the room that left the room can reach you.
Okay, and I think you've my email address in the chat window. If I'm happy to take any questions. I can't remember if you recorded this. Is that correct, or maybe the recording had to be stopped?
Yeah. We're recording it. Yeah.
Okay, great. So yeah, I mean, you have it recorded. So if anybody has any questions, just send me an email. I'm happy to respond. I can also jump into a Zoom call if you want more information. But
thank you very much.
My pleasure. Hope everybody's safe and take care.
No, everything is okay. Thank you.
Good. Bye-bye.
Bye.
trying to develop a virtual creator that has a human-like behavior. The problem with the current proposal is that they don't include a lot of dynamics, like bottom up or forgetting. They don't include these abilities to their models. For that reason, we propose as architecture that supports multiple inputs, includes different memory dynamics, like forgetting, and is based on neuroscience evidence, and it's a distributed system. So all the system is implemented using different processes. The last 50 years, a lot of research groups have developed cognitive architectures using different approach. The idea of the cognitive architecture is so we can endow the creators with human-like behavior. In this section, we analyze different cognitive architectures that contains some type of episodic memory or that's similar to episodic memory. For example, SOAR is an architecture that is that helps reasoning, planning, execution. The SOAR architecture has a lot of episodes with timestamps. So thanks to this, we are able to retrieve previous following episodes. The thing with SOAR is that they don't have like a specific episodic memory or forgetting. They don't have forgetting. IQ is an open system, 53 freedom degree humanoid. This system stores the memory image. When a new image arrives to the system, it compares this image with the stored ones. If the image is similar to other, it retrieves the similar image. If not, it will encode this new image and store it. Then we have ACTR. ACTR is cognitive architecture. The idea of ACTR is understand the human cognition. ACTR has a unit of memory named chunks. These chunks includes facts or meanings. It's similar to the idea of episodic memory, but it doesn't have a specific episodic memory. Then we have Libra. This architecture is trying to emulate cognition. Also have a lot of scenes, timestamp. LIDA has a declarative memory system that splits between autobiographic and semantic information. So similar to episodic, but doesn't have like a specific episodic memory. Clarion is an architecture that is inspired in psychology, so it doesn't have brain areas, but it has definition of episodes that have timestamps. So as I mentioned before, this proposal is based on biological evidence. So this is how we work. We work with model. First, we identify all the brain structures that have some tasks related to episodic memory. Here you can see that we have all the areas related to episodic memory. Then we identify the relationship between them. For example, which one is the input of the other. Then, okay, now we know that they have the episodic memory functions, the relationships, the order of the flow. And then we try to add another classification to this structure. For example, in this case, we identify the structure that help with the process of the stimulus, the one that are focused on episodic memory, the one that helps with working memory, and the one that helps with the process of the stimulus, and other structures. Okay. Now that we identify the structures, here, for example, and now we identify the tasks that each of these structures help For example, we have the visual system. The visual system is a set of brain areas that helps with the identification of object features. It's out of the scope of this paper, but in theory, this helps us to acquire information from the environment. And in this model, we use the visual system to capture the image and also stream it. Then we move to the parietal cortex. The parietal cortex helps us with the stimuli processing. So that means it takes the information that we have from our environment and it segments the data. It helps us with the parietal cortex to identify the amount of objects that we have, the location that where they are belong, the location like values x, j, and these values are from the center of the image. So now that we have, we know the amount of objects, the location of them, we're using structures like ITC or inferior temporal cortex. This structure help us to, we know that there is something, an object. Now we need to know the class or the category of this object. So for example, we can know, it's a bunny, a ball, or something. So this structure, after we send like the main feature, it will identify the object and it will reply with the class that it belongs. Then we have the perennial cortex. The perennial cortex helps us. It's the first one that helps with the episodic memory. This will help us to create a relationship between the objects. For example, if we have two objects in the same scene, that means that they have some kind of relationship. So we will store this relationship in the system. So in the future, if we identify one of these objects, we can recall or retrieve the other one because we know that at some point they work together. The perennial cortex also helps us with the it's an object gateway. Gateway, it means that it helps us send information with one area to the other. And then we have the internal cortex and subincum. These two areas also are getaways. These areas in particular have another task for other memories like semantic, prefrontal cortex. But in this case, only help us to send information to one area to another. Then we have the hippocampal areas. The hippocampal areas help us with the encoding, the creation of the scenes, the relationship between the scenes, between all of them. And one of the areas between the hippocampal cortex is the digit, or the status here. This one helps us create a pattern that will help us store the scene that we are capturing. So we have the string for the information that we have for the visual system, and then thanks to areas like the status series, we can store this information in the brain, so we can restore it later. Then we have CA3. CA3 also helps us to create, to assign a pattern to the scene that we are having, and also with the retrieval. That means that when we are trying to retrieve episode, we have a part of a pattern. We can use this part to find similarities in other episodes, and then we can retrieve it. CR1 help us to create association or relationships between multiple scenes. Thanks to this ability, we can create plans because we know that this scene or this episode always happens before one or after other. So we can create like a relationship between them. And also help us with the storage of this episode. Then we have the prefrontal cortex. The prefrontal cortex main abilities or tasks are related to the working memory. One thing that I forgot to mention is that memory is usually they split the memory in different systems, so it's easier to study and implement. Majority they are very connected, so they are very interacting all the time. So for example, here the prefrontal cortex helps us to store current episodes that we are needing in this time for a short period of time. Also help us store key objects or information that we need to restore episodes. Also keeps help us to store information enough time so we can create the relationship and other things that we need for the other areas. As you can see, we have a lot of modules that are working together. Each one is we can see them as a process that are interacting. The way that they interact is with package. Each package, we name them spikes. These spikes contain information related to the information that we want to send, right? The spikes can contain object names, object class, relationships, ubication, relationship between scenes, or a series of a sequence of scenes. Here we have, okay, now the information is running. The episode memory has 3 main flows. The first one is encoding or storage process. In this process, all the information that we are getting from the environment, it's we took the information and we create the patterns, we add classes and relationship, all related to encode and store. Then we have the bottom up. Here is when the brain is, or the artificial model is trying to recollect or retrieve information that is related to the things that we are getting from the environment. So that's the agent is not trying to recollect this information. It's a natural function. So we are getting all the related information. We store that in the working memory just in case that we need that for acting or for any decision. It's just in case. And then we have the top-down approach. In the top-down approach, the agent is trying to recollect or retrieve information. So it tries to recollect information that is not part of the thing that we are getting from the environment. So we have this external input that is stored in the working memory. Then we use this as a keyword to recollect it. The implementation is 3 layers. The first one is a Unity model, where we are getting when we have all the objects, the scenes, and the creature. Then we have a Python layer. This Python layer is a perception system that helps us identify the main features of the objects that are in the environment. And then we have a middleware. This middleware is implemented by the research group. This middleware tries to each brain area is like a server that has a lot of services. The services are the tasks that are doing the episodic memories. We have 2 test case studies. The first one, we are trying to test only the memory. Here, the virtual creature, we put the virtual creature in an environment. So first, the creature is trying to learn the environment, the objects, the relationship between everything. Then we put the same virtual creature in the same environment. The idea is to see if the creature is able to recognize that, oh, I have been here before, so I don't need to store this again. I don't need to because I already know this. And the third phase is when we ask the virtual creature to find or recollect information related to one object that was in the environment. So here we're trying to see if it is able to recollect as we expect. Second scenario, we have 9 rooms. Each room has different locations and objects. The creature needs first try to learn, identify the objects in each room and the location of each one. And then, okay, again, we leave the creature in the same place. We try to see if it's able to identify things, recollect, and reduce the amount of encoding and storage. The results of the first experiment, we noticed that the creature is able to first retrieve scenes. Then we play with the similarity threshold. First we use a .5 And with this one, recollects around 19 different scenes. So similar to this. And then we increase the threshold to .8. In .8 only defines one scene. So the one that we are actually using. And the second experiment, first the agent is learning everything. And in this scene, we also ask the agent to find a specific room and starting from another room. So the creator needs to find or identify the steps needed to move one to the other. He already knows. The results here is that the agent is able to list all the scenes that help move from one scene to another. The execution plan, it's the action needed to move from one to the other. And then the reduced execution plan is where the system identifies that has multiple scenes, multiple execution steps. So they reduce the duplicates and has the better speed. With the results, we are able to say that we have a specific memory model that can encode, store, retrieve, and forget. It can create multiple scenes and object relationships. Information can be general or specific, and the outputs can be used in another functions like planning. We noticed that because we are using only 2 layers, we have a lot of ambiguities. For that reason, we identify that we need to add more print-areas. These print-areas will help us create more information. This information could be more specific, so we can reduce ambiguity. And we need to combine with more complex functions like decision making or attention and motivation, so we can have goals, different goals. In conclusion, this is a base on psychological and neuroscientific evidence. It's a modular and distributed system. That means it can run by itself or it can be part of a distributed system. It's useful for multidisciplinary domains. That means we can help, games, or we can understand the human cognition. And it's part of architecture. But thanks to Consortium for the financial support and
any question?
Hi. I was wondering, when we talk about episodes, there are the beginning of an episode, the episode takes some time to happen, and then at some point it stops. How do you make this transition from the beginning to the end? Do you have ways for detecting when an episode is starting or when an episode is finishing?
We use identifiers. We use timestamps and identifiers. So we know which one is the first one, and the next one has the next identifier, right? That's the way we are at least identifying that one is before the other. The timestamp and identifiers. And when we know that something start or finish, it's more like what we are looking for. In this point, for us, when we're retrieving by objects. So, for example, maybe the first 4 scenes doesn't include the object that we are looking for, so we are not including it. We are including since the object is present, and also the object is present. When the object disappears, we could retrieve. We are at this point of the architecture, everything is related to the object and its relationships.
How do you deal with something that has intrigued psychology and cognitive neuroscience for decades? That is, especially in this kind of memory, that is the repression of memory, not the forgetting, but the repression. I can remember not because I forget, because later on I will remember when I'm older. But then in that
stage of my life, I can recall something because I repressed.
In this model in particular, we are not including things like motivation, attention, or emotions. And in this case, when we include them, since the beginning of, we start with the memory model, we use the approach that we have always information, but we lost the connections. So the information is always there, but we lost the connection. When we're forgetting, we lost connection. So when we retrieve something that is very, very easy to find, like compressed memory, it's because a lot of things combine at the same time. So when we are retrieving, it's the only one with the purpose code. So it's the more simple, but we need to have a lot of things at the same time. So right now, the idea is to add the episodic nervous promotions to this approach. So when we store this in the episode, it will include the feeling that has in the same time. So when we also can retrieve the episode by the feeling, so not just by the objects. And another thing is because we are implementing the forgetting, it's when we retrieve the episode. Each time that we retrieve, we are going to reduce the threshold, so it will be difficult to find. But just remember that each time that I use it, I will press reduce or modify also. Because maybe when the first time that I stored the episode, I was very sad. The second time I was like, eh. So maybe the amount of sad will be reduced. So the next time when I'm very sad, maybe it's not going to be my first option.
Another question? Okay.
Is there a software available that we can have access to have a better understanding of how this works, and is it possible to have access to this software?
Yes. The way that is implemented is because it's a distributed system. We have the middleware and we have the definition of each area. So yes, we can access it. Yes, I think I don't know what it is, but that's okay. But yeah, yes, since in the Unity, how things are in Unity, the perception and then the middleware. That also helps. Thank you.
Okay. Thank you, Karina, for your presentation. We need to proceed with the next talk. It's entitled Functional Framework of the Visual Sensory System Based on Neuroscientific Evidence of the Ventral Pathway. It will be presented by Luis Adrián Parra.
Ahí está. No sé. Sí.
Hello everyone, I will present a computational framework of the visual sensory system based on neuroscientific evidence of the ventral pathway. My name is Luis Parra, and we make this work also with Daniel Madrigal and my advisor Felix Ramos from Simvestab Guadalajara. So what this work is consisting? It consists in we propose a computational architecture for visual processing with low and medium level features, integrating the following aspect of vision, that are the transduction, the processing of color, shape, and the early stage of the motion processing. So this is the outline. So we will start with the introduction. So we know that through vision, human beings can process light stimuli to create an internal representation of our world, to create an internal representation of the environment in our mind. For example, this image we can see. So in the brain, the visual processing is carried through these areas that are retina, lateral geniculate nucleus, and the visual areas. It's important to say that we are not making object recognition. We are making visual processing system that is like analogous to the feature extractions in artificial intelligence and in computer vision. So generally, this processing is divided in two ways, that are the ventral pathway, that has areas with neurons specialized in the high details of the object, and the ventral pathway is in charge of the object recognition, and the dorsal pathway has neurons that are less sensitive to the details of the object, but has neurons more sensitive to the motion. And in the dorsal pathway, we achieve the object location and motion. So the processing performed by the brain, by the visual areas, is hierarchical, where low-level features are assembled into features of higher complexity. For example, we see that in the area V1, we start with the selectivity of the oriented edge. So in V2, more complex features are processed, and finally in V4, we have the selectivity of very simple shapes. And then the hierarchy is advancing. For example, in area IT, we see like some selectivity to more complex stimuli and faces, and I don't know what more. And the visual sensory is important because it provides valuable information to other cognitive areas and systems to perform the high-level visual processing functions. We can see also we can say that also the difference between sensory system and high-level visual processing or perception is like here we make more unconscious processing, and perception is more conscious. And okay, the visual system is providing information mainly to attention, perception, and memory. So in the problem definition, the understanding of how the human visual system is working is a still open problem in neuroscience and in computer science. There is no unifying theory of how the brain performs visual processing, visual sensory processing, and the development of a computational architecture that integrates multiple aspects of vision is still a major challenge. And speaking more about computer models, some computer vision models are limited to certain type of tasks. They are very good and very efficient in some specific tasks, but to create a general vision model is still an open problem here in neuroscience and computer. And in the case of bio-inspired vision models, they have a specific scope, or they cover the explanation of a very specific vision phenomena. And another thing is some models are not considering the interaction with more cognitive functions, and we need to make important that this model also is part of the cognitive architecture that we are developing here in Sinvestar Guadalajara. So our approach is through the study of neurons in scientific evidence about different areas, their function and communication. Is possible to design a computational framework of the visual processing system. And this will make possible to provide an intelligent agent with the information similar of how the human being process this information, and come closer to obtain human behavior, obviously, also with the integration with other more cognitive functions inside a cognitive architecture. So starting with the design of the model, the approach that we are using more is using linear and non-linear filters to create feature maps. Maintaining the information in a modular and transparent way. So first, based on neuroscientific evidence, we designed this diagram, this conceptual model where we see the components that correspond to the visual areas, and the subcomponents correspond to the type of cells, like type of neurons in that areas. And then we have the execution diagram with the functions. And speaking about the aspect of vision that covers this model, we see the parts that correspond to the transduction, the color processing, the shape processing, and the early stage of the motion processing. So speaking about the color processing, we start with the RGB image, and then we transform the RGB image, the RGB pictures, in a LMS space that correspond to the activation of the cones, like low, medium, and short frequencies. And then in the lateral uniculate nucleus, the single opponent of operations are performed to convert to EKL space. And then another opponent process, in this case in V1, the double opponent process is performed, and we see we use more different options here. And finally, in V4, we obtain a map of the color regions that are categorized. And this processing of color is also important because if we integrate with models like attention, we can have more functions, more filters, because for attention it's very important to obtain this color scheme more close to the neuroscience instead of a normal RGB picture. And now, speaking of the shape processing, we start with the obtention of the oriented edge maps. So we make convolutions with Gabor filters on the input, producing the orientation maps. We use two phases of the filter, like symmetric and antisymmetric, in order to, in the complex cells, obtain the spatial invariance of edge using the energy zone model, like energy. Yes, we assume the inputs, and then we obtain the invariance. And then in the hypercomplex cells of V1, we obtain the selectivity of the edge with a certain length. And with, for obtaining that, we use end-stop filters, where the edge terminations are filtered. And this is useful for obtaining more important or more relevant information in the picture, and also helps to obtain the figure ground segmentation in the future. And now, speaking about the selectivity to specific angles in V2, we use the orientation maps to obtain the corner with the specific angles, the angles. The operation is very similar to the multiplication. And then for obtaining the angular rotation invariance, the maps of angles of the same aperture, but different directions are merged. Also, before we obtain the selectivity to specific curvatures, where we group curvature stimuli with a certain radius and directions are filtered out. This is very similar to the corner detections, but here we can obtain a wide range of activations. And for also obtain the rotation invariance, the stimuli of the same radius and different directions are joined together. And then for obtaining the simple shape selectivity, we use the corner and the curvature information for the simple shape selectivity, where we combine these maps, and also there is an operation very similar to the multiplication, where we obtain the activations when these patterns are matching. And also we obtain the scale invariance, where we have different simple shape maps of different sides, and they are joined together. And then we obtain the segmentation, where a segmentation of the detect simple shape is carried out, where we use the shape for obtaining for obtaining the simple shape. Now we will make a segmentation of the original picture of maybe from the retina, or we can use, for example, the V1 maps or something like that for make the segmentation of the shape. And also for our chip, the segmentation with scale invariance is the same, but we use different size of shapes. And now, speaking of the first stage of motion processing, we use the information from the oriented edge from the complex cells of V1 to make a buffer of maps. So we obtain a map of oriented edge that are moving in a perpendicular direction, and this will be the input for more complex processing, for example, in the area MT and MCT that are detecting more complex motion. And also we are considering feedback mechanisms inside the system. So the system can receive a modulation input from an external system, and how it will work. An external system like attention or perception can send a map also, a modulation matrix, and this signal will be propagated to the successor maps and in some proportion to the previous map. So every map of the maps of our system are capable to propagate a signal to the previous map. So in the future, we also can have effects of the context modulation, for example, from the area of perception or from perception. So watching some experiments and the implementation was done using the research group framework presented in the previous presentation. Was programmed in Java using OpenCV library. Yes, or Windows is intuitive, is very easy to use. The main data structure of the maps or matrix was designed as a node of graphs to support feedback connections like we have for the previous and the next nodes. And we can see the results. We see the transformation of the color processing. And now, speaking of the shape processing, we see how the orientation maps are generated. We see the simple complex cells and the hypercomplex. And the importance of the hypercomplex cells here is we can see a lot of noise are filtered, and for example, in the tree, we only can see more the determination or the real contour of the tree, and it's very important for the figure ground segmentation. And also we can see the corner selectivity is better to see in the simple shape in the fields, and it's very important for detecting like corners that provide more relevant information compared to the only edge. And also we can see the selectivity to the curvature. So we have these stimuli that are circles, and we see like very interesting result here. So depending of the radius, these circles are filters. These circles are filters. Also, like very clear result was made to the simple shape selectivity. The study case here is very simple, but we can see very clearly the activations that are corresponding in the center of the shape. Also, we can see the edge motion in V1. It's a very simple case. We need to make more complex case about this motion processing. And in conclusion, making a little bit of discussion on what we need more, we need to make more research about link various aspects of vision. We talk about discover some aspect of vision, but for example, there is no binding of color and shape processing. You can see like the color processing goes in one way and looks like very isolated. And also we need to bind them, for example, more functions between the dorsal and the ventral pathway. Also obtaining intermediate features such as corner and curvature needs further research in this proposal. More advanced motion processing needs to be considered, as well the stereoscopy. The effect of feedback loops needs further development, and also exemplify in a case study what is the effect of the feedback. Also, the training for the shape patch in before is considered in the future, because when the information advances, the combination of patch becomes exponential. So many models, like for example HMAX or convolutional neural networks, they use like training for make these patches in the high areas. So it's considered. Of course, a comparison with neuroscience models should be considered, because the study case here was only like showing the results in the matrix, but we need to compare more with neuroscience. And in the conclusion, this work presents an initial proposal for a computational architecture for visual processing that covers various aspects of vision. Is able to process early and middle visual representations without the need for training. Considers integrations with other functions in a cognitive architecture. It maintains a modular and transparent approach, so external functions can access to that information, and the integrations with other cognitive systems will allow the creation of more complex study cases. So that was all. Thank you for your attention.
A question? Okay.
It was a very nice work, and I was wondering, considering the effort that you have put already in the development, how much effort do you think it will be necessary to include stereoscopy and 3D processing in the system that you are doing right now? Do you think it's something like double the work that you already have done, or the triple, or 10 times? How do you evaluate the amount of work that will be necessary to have 3D modeling instead of just 2D modeling, just like you have right now?
In fact, we are right now developing this model, this framework for 3D. I mean, for stereoscopy is not too much. Is not too much considering the compatibility. For example, there are also for stereoscopy, there are the energy models that are also using information from the edge. So the models are very similar. However, the stereoscopy has the problem of the correspondence problem. So we need to use a lot of units, a lot of spatial frequencies for reducing the noise. So we are implementing that in the early stage in V1. However, it's slow because we use a lot of spatial frequencies for the noise. So if the models of stereoscopy are compatible, is not a big work. The big work is more about the connections and optimize the model to be faster.
And how far you think it is to making a connection from what you're doing and the work that Karina has presented in the other presentation, putting these things, transforming that into episode information that could be stored in episodic memory, for example?
This also depends of the perception system, because my system is giving information to the perception system, but I am not doing the high-level visual processing. in the last year, this was also integrated with the perception system, but yes, depends. This depends of this system and the integration with the perception system in order to first having the necessary features and then having the recognition of the stimulus. So sounds like it's not too far, but it's also far at the same time. So it's a very tricky question.
Another question? Okay, no more question. Thank you, Luis.
Good afternoon. My name is Doctoral, and I will present my work, which has by title "This Perceptual Circuit for the Generation of Autonomous Responses to Virtual Creatures." Okay, so when we speak about taste, meaning human or any kind of creature taste, it's quite self-explanatory because it's something that we all experience day after day, and also something that we are able to describe. So, however, even that, it has been a real problem to simulate taste, sensations, as well as other human processes. And one approach to this problem is cognitive architectures. They allow us to address this kind of problems by abstracting cognitive functions and processes and build models that can be implemented. Now, even with this approach, there is not any cognitive architecture that considers taste into its model, and that based on that provides autonomous responses on virtual creatures. So if we look to the literature, only one cognitive architecture considered taste, and is called Nomad. So Nomad was implemented in a robot called Darwin. Is that curious robot over there? Okay, how Darwin using Nomad considers taste? Basically, it uses artificial taste sensors based on conductivity. So they make Nomad to pick up objects using an electromagnet. Is that like circle over his head? And it was controlled by a nervous system. So it can perform the task of sorting conductive blocks of a certain color, which is quite the bad taste, and non-conductive blocks of another color, which is the good taste. You can see the blocks right over there. So if high conductivity or bad taste is detected, it activates the taste cells that excite the avoidance reflex. This causes Nomad to move away from that particular block or object's direction. So this actually relates to the problem that there is, again, not much or not any other cognitive architecture that allows us to process custodial information, and that can be implemented on virtual creatures because this was implemented on a robot, and it was designed specifically for this robot. So we cannot generate any kind of other responses. Okay, so the objectives for work are first, the identification of computational works that address affective processes oriented taste. Then analyze neuroscientific information for build an informant model of perceptual circuit of taste. Then generate a perceptual taste circuit that allows generating autonomous responses and learn effective taste evaluations oriented to perceived stimuli. After that, of course, implement the model using a distributed platform. And finally, test the system and validate the results. Okay, so the first step was identify the brain structures involved in the process. So everyone who research something in this field will realize that the information from the different perspectives, psychology, neuroscience, biology, is wide, and sometimes it's even contradictory between each other. So in order to identify the most important brain structures involved in the auditory circuit, we grab the most relevant proposals, and we identify those structures that were clearly involved. So after we identify those important structures, we came up with this conceptual model. So we built this model using the same approach, actually. So let me do it quickly and explain the model. I'm not sure if you are able to see it. It's a little bit small. But basically, everything starts in the oral cavity, which is the circle in the bottom. We have, of course, taste buds in oral cavity that acts as sensors. So all the taste buds that we have passes information throughout the cranial nerves. We have 4 cranial nerves that passes information to the brain. Number 5, number 10, number 9, and number 7. So only number 5, which is the tegmental, passes other kind of information from the mouth as well. Passes temperature, passes pain, for instance. So all this relies in the NTS, the nucleus of the solitary tract. And this acts like as fierce relay. It just grabs the information from the cranial nerves. Okay, then the information is passes to the BPMPC, is the nucleus of the thalamus. And then the information is split up in the insula, which is the primary gustatory cortex. Is if you go over the literature, it is named like this because this structure is actually the one that identifies the different kind of flavors that we have. Also, it measures the intensity of the flavors as well as other kind of measurements, along with several other sensory information. Also, the information is passed to the mesolimbic system, which the lighting circuit takes place. Then the information is passed to the OFC, which is like the secondary gustatory cortex. There, the quality is measured, the quality of the flavors. It takes information from the mesolimbic system, from the metabolic system as well, and from other sensory information. For instance, olfactory, visual, and texture. So after we identified and build this conceptual model from the neuroscience literature, we built this proposed model. So you will find that each module has an abstracted functionality of the perceptual model. In this diagram, you see white black boxes. So these black modules are parts of the system that we did not formalize because they were too complex to do it. So we treat them like black boxes that just provide values or inputs to the other systems without real processing. So first we have the auditory input view that just provides auditory information to the system. Then we have the sensory receptor that is an abstraction of the taste buds. This module converts the perceived stimuli into taste signals within the virtual creature. They modify the intensity over time and send information throughout the different channels simultaneously. Then the NTS acts as a gateway because it just encodes the taste signals coming from the different channels and creates a single flow of information. and then send it to the module of selective preference. The selective preference actually remains as a black box due to the lack of information in literature, but we decided to keep it there. Then we have the intensity evaluation module that is like the main module in the system. It alters the flavors values depending on the levels of suppression that exist between them. So for instance, if you as a human taste sweet and bitter at the same time, you're going to find that bitter suppress sweet and sweet suppress bitter as well. So these kind of suppressions take place in the intensity evaluation module. Also, there are some cases in which the flavor is increased. For instance, when you consume, I don't know, umami and sweet, both of them increase in intensity. Then we have the quality evaluation. This box is responsible for evaluate quality. It's different, the intensity or the quality, and both of them are correlated, but is a different value. So actually we decided to keep this module as a black box to the real complexity of the module, because in order to achieve a quality evaluation, you need to have other kind of information, like emotional information. You need to have like needs, motivations, and all this kind of information relies on quality. So that's why we decided to keep it as a black box. Then we have the regulatory assessment. This is responsible for regulating the homeostatic state of the virtual creature. And we also remain as a black box because we didn't actually develop a homeostatic state in the virtual creature. Okay, then we have the emotional response. So based on the information provided, it gives an emotional response. So the output of this module is an assessment of likes or dislikes towards the flavor states by the virtual creature. And lastly, we as an output, as actually autonomous response, we have the facial expression that processes the emotional response and generates an actual expression in the creature that denotes the level of pleasure or dislike. So I'm not going to go over the formulas of each module because the short time that we have. But I just wanted to explain each module as separately, and just to point that we have a modularized set system. I was supposed to change this. Okay, so for the implementation, for implement the model, we create a distributed system based on a microservices architecture. This allows us to process the flows of information simultaneously of the different modules of the system, giving, of course, a more realistic ecosystem in general. We did not implement the black box modules. We just inverted their values. Okay, so in order to test our system, we create a very simple case of study. Basically, we grab two flavors that both suppress each other. Is like actually the example that I gave before. We pick sweet and bitter, and we test our system providing the platform with different initial intensities. We also consider an affective value for each other of the flavors, just to make them more like realistic. Okay, so this is how it looks, the initial parameters. Obviously, in order to test the system, we needed to configure the whole environment with a set of values. So these are the ones that I consider most important. We have the max time of flavor in taste receptor. This is when you consume something, when you taste something in your mouth, the flavor remains for maybe between 3 and 16 seconds. So we hard code that value. We also have the alteration rate for sweet and bitter, and the alteration rate for bitter with sweet. And this is when you taste sweet and bitter, there is a suppression level between each other. So obviously it's different for each people, for each person. But in order to test our system, we decided to hard code these values as like this. Finally, a function for flavor times intensity. This will be more clear on the results, but basically, again, when you taste something, it remains in your mouth, and that has a function. So normally, the function is something like a Gaussian. You will see a graph like this. In normal persons, obviously, it's not like each of us has the same function. So to test our system, we provide this function, which is basically a curve. Then we provide emotional responses, which in this case is just neutral, pleasing, or aversive. And emotional responses threshold, that is basically depending the value of each flavor, it will provide a response. So these values, these thresholds are these ones. And also we set as some conditions. What happens when bitter is greater than sweet and when sweet is greater than bitter? Because if you taste two flavors at the same time, someone will be greater than the others. So depending on which is greater, you need to handle the output differently. Okay, so this is how our results looks. I know that it's small, but super small. But let me just try to explain it. In this table, you will see 3 rows. That's because we set the max time of the flavor in the mouth as 30. So this is the seconds that the mouth has that flavor. And okay, I'm not going to explain each column, of course, but you will see how the intensity of the flavor changes over time and over the circuit. So at the end, we have a response, an emotional response, that is translated in a facial expression. Okay. Okay, I know that it's a little bit hard to explain graphs that are this small, but basically in this graph, we graph 3 important things. One is how the initial flavor, we have 2 flavors here, bitter and sweet. So red ones are bitter and blue ones are sweet. And how the initial is suppressed by the other one. So you see a red line, 2 red lines, one over the other. So that's because the first line is the initial intensity that was suppressed by the blue line, which is sweet. So the bitter just go down And this is the graph, this is the meaning. Also, we have a green line, which is the total impact. So once you have two flavors, you need, at the end, you need to have an impact in the creature. So it could be good, could be bad. So that green line represents the total impact of the two flavors. And the yellow line is just the threshold. So the first 0.2 seconds was neutral response, and after that was just aversive, because we passed in this particular test a high percentage of bitter and a lower percentage of sweet. So in the second graph is actually the same test. We pass a high percentage of bitter and a low percentage of sweet. But we also provide an effective value for each flavor. So what happened was that the thresholds that we have just move. And if in the first case we have a neutral and an aversive, in the second graph we have a neutral, pleasant, and aversive, because the effective values that we set was that the creature in that moment liked the bitter flavor. So basically that's the meaning of these graphs. Are the same test, just with different effective values. In the first one, we don't have any effective value for bitter or sweet. And the second one, we have an effective value for the bitter. The creature likes the bitter. Okay, and this result is pretty much the same, but the difference is that we play with the sweet flavor. So in this case, we first provide zero effective or not. Let's say like it's like the natural behavior of the human in the first graph, in which if you consume sweet, you will have first over the time a neutral response, then a pleasant response, and if the sweet is too much, you will have an aversive response. And in the second graph, same test, but now we set a really high effective value for the sweet. So now it doesn't matter how much sweet the creature consumes, it will be pleasant always. So the same test, just I move the thresholds with effective values, changing the effective values. So the conclusion is that the proposed model is functional in calculating intensities for virtual creatures. It also gives natural behaviors, even if the tests were quite simple. Also, the proposed algorithm were inspired by the evidence collected from the processing of the different brain regions and the general structures of the human body. And it is possible to incorporate the proposed model into a more robust system that allows the virtual creature to behave, take decisions, and learn in a more natural manner. Actually, this small model has very simple values and very simple functions in order to just taste it. But it can be, of course, fitted by more robust systems and more robust algorithms. So I think that this is so. Thank you very much.
Thank you, Daddy. We have time just for one question. Okay.
Hi. I was wondering that the modeling that you have developed can be very useful, for example, in food industry for making food quality control or things like that. Particularly one part of food industry that is wine evaluation would be very interesting to have a system that could make evaluation of wines depending on taste that you get from the wine. But I was thinking, what about the sensors? How to get real sensors for these 5 features that you, okay, in a simulation you can do that very easily, but in a real environment, how can you get this information from the environment?
Yes, actually, that's actually the hard part, the hardest part. That's why we don't have many cognitive architectures that achieve this. And that's also why we did it for a virtual creature, because we don't need that kind of sensors, of course. If in some point of life we build this kind of sensor, this model could just be incorporated to that information, of course. But now we don't have that, so that's the problem, and that's why not much cognitive architectures content with taste.
Thank you, Dario, for your presentation.
No es
Me perdí aquí, pero ¿qué es el? Profesor Ricardo.
Bien.
Profesor Ricardo.
I think that this is fine.
Is this one? Or
This one?
No, this is for today. This is not for no. This is for our extra. It seems that you have stored that into a desktop or a directory. I don't know exactly. Side address. It was open somewhere. I've seen it. Yeah. Yes. Or you can just download it again from the email.
No. Because just I didn't know those because I am not very used to Windows. Francisco, puedes ayudarnos.
Pero estaba en la otra computadora, ¿no?
¿Qué hago? Es su Mac, es su Super Mac. Sí. Entonces, ¿lo puede hacer desde acá? Sí.
Entonces, déjame ver.
De hecho, es la que está compartiendo pantalla, Félix.
¿Sí? Las dos son Félix. No, pero entonces primero dejo de compartir, ¿no?
Sí.
Tienes que
dejar de...
to drop this down.
Yeah. Please. Yeah? Okay.
This is the oldest one. It's the other one.
Okay.
Why you are not having the full?
We don't know. We don't work here.
I see.
Está raro su Mac, ¿no?
Sí. ¿Y cómo le pongo las fechas? Which one?
96. Yeah, this one.
Okay. No, ahora compartir.
Tenemos que poner en full screen.
Yes, to share. Share. Where is that?
No, en los puntitos.
Está en
Los puntitos.
tres
Los tres
puntos.
puntitos. Ahí.
Sí.
Ya está.
And is this? Yeah.
Pero para poner en tu screen.
¿Cómo se hace eso? Francisco.
Visualización, presentación
de Play.
pantalla completa. Sí, excelente.
Entonces, aquí.
¿Dónde está el micrófono?
Sí. Ahorita cuando acabes de presentar.
Está bien.
Good afternoon. My name is Tanya. I'll be the chairman during this presentation. We shall start with Ricardo's presentation. Are you ready to start?
Okay. This is a work that is done by a lot of people. You can see that I'm not going to talk about everyone. It is a part of our hub of artificial intelligence and cognitive architecture. And the idea is to talk about our visualization tools for monitoring and debugging a cognitive architecture using CST. This problem of having a visualization or debugging tools is actually an essential during the development of intelligent agents, because after the agent is already done, well, you don't need to get too much onto the details of the architecture. But when we are developing an architecture, there are many situations in which we would like to tune the architecture and put a feature that is not there, or to fix something that is not working on the right way. So we need to have a mean for visualizing what is happening inside the architecture. Okay, so these tools can be used with the double purpose, with the purpose to debug when you are developing the architecture and to enhance the cognitive architecture that is controlling the agent, but it can also be used for describing the inner mechanisms that the cognitive architecture has to newcomers. So if I created the architecture and I want to explain how it works, nothing better than having a visualization tool that I can enter into the details of the architecture and explain its inner mechanisms, okay? But unfortunately, there is just a few discussions about this issue in the cognitive architecture community and literature. We don't find too much works talking about that. Well, in our case, I'm going to present what we call the Mind Viewer, which is a visualization tool for monitoring and debugging cognitive architecture. It was constructed together with the CST, the Cognitive System Toolkit, that is being developed by our group. And it encompasses a variety of charts that are used to monitor the inner details of an agent's mind. Okay. Okay. So first, let's talk about some of the other debuggers and viewers that we can find in cognitive architecture. This is the case of the SOAR debugger. So SOAR architecture is quite well known, and it provides a debugger. This is a screenshot of the SOAR debugger, but it's not exactly easy to get into the inner details of the working memory elements using the SOAR debugger. You need to have to insert text comments on the GUI, and then you need to go step by step, seeing each working memory element at a time. And at some point, it's not so easy to see the whole picture of all the different pieces of knowledge that I want to debug. So there is a debugger, yes, but well, maybe there are some problems in using it in practice. Okay. This is also another example. This is the LIDA framework viewer for the LIDA cognitive architecture. It's a nice viewer. It provides a lot of features, but again, there are some of these features that are not so well documented, and so it's not so easy for someone that is not actually aware of the full inner principles of the LIDA cognitive architecture to use the viewer. it is useful, of course, but not so easy to grasp the information that you want from the LiDAR framework viewer. And then this is our proposal for our mind viewer. So we have actually created two different versions of the mind viewer. This is what we call the desktop version of the mind viewer. It was created for applications that use CST in a desktop because it uses the Java features to allow us to get into the details of each of the pieces of knowledge that we have inside the architecture. We can assign different tags for these pieces of knowledge, so we can divide it internally into sensory tags or drives or more higher knowledge pieces of ideas. And you see that it can be very full of features for getting into the inside part of the architecture. This is another example of the same. We can have many different views with different windows where we can focus on the information that we are interested for our evaluation and for our debugging. Okay, this is also another example. This particular example is for information coming from a laser scanner sensor from a robot. And so it would be useful to put all of these laser points at the same time so you can have an understanding of what is actually the robot view that is entering into the cognitive architecture that will be further processed by the architecture in order to create some model for the objects that it's able to sense. Okay. This is another version of the same mind viewer that is actually a web application. More recently, we just realized that Java might not be available in all these situations. For example, if we are trying to debug using a smartphone or other kind of device that don't have Java available, maybe having it available on a web app would be more convenient. And then we generated a web version of the mind viewer that could be used, so we can have many different kinds of maps, many different kinds of graphs that we can take. All of them can be taken in real time while the architecture is running, so we can debug not just with the logs. We can use the logs for making this monitoring, but we can also debug in the real time when the architecture is performing. Okay, this is important to talk why it is a little bit connected to CST. Well, CST, we have this notion of having codelets and memory objects. And everything inside in a CST made cognitive architecture, we are going to see codelets and memory objects. And this is the reason that it's very easy to connect that with the visualization, because we can get information about each of the codelets, and we can have information for each of the memory objects depending on the data that we are wanting to investigate. We can use these codelets and memory objects to create full-feature cognitive architecture. So we can talk about sensory codelets, perceptual codelets, attention codelets, and then we can debug that with the mind viewer. Okay. In the paper, we have used an example that is an application example to illustrate the use of the mind viewer. In our example, it's a quite simple application that is made with the Iowa gambling task. The Iowa gambling task is a neuropsychological task to simulate personal decision-making under uncertainty of premises and outcomes, rewards, and punishments. Well, the original task involves a participant that is instructed to maximize its profits while choosing repeatedly one card from any 4 decks. Each card in decks A and B has a $100 reward on it, while $50 reward on each card in decks C and D. As punishment also occurs, decks A and B are equivalent in terms of total loss value. However, they are applied at different schedules and intensities. In deck A, the punishment is a smaller magnitude but more frequent, whereas in the deck B, the punishment is of higher magnitude but less frequent. The same happens between deck C and D. Also, the cards penalties are unpredictable and the participant does not know the limit of the chosen cards. The intention of the task is that reward and punishment are arranged so that decks A and B with higher gains penalize more, leading decks C and D with smaller gains be advantageous in the long run. Well, our version of the experiment is not made exactly with the decks, but we have created an artificial agent that was implemented by CST, and we have created this virtual scenario where the robot can move around and can reach the different points where it can get energy from these points. Okay, the agent is a robot that can move towards a power station and recharge, receiving different kinds of reward in doing that. The goal is to reduce the distance between its needs and its homeostasis states. To do so, our agent is equipped with sensory, perceptual, and decision-maker codelets following a cognitive architecture using this CST. And this is basically our architecture. You can see that we have many codelets. These are the rectangular blocks, okay? And we have many memory objects, which are the circles in the architecture, okay? I'm not entering into the details because they are not so important for the illustration of the viewer. But it is important, for example, to know that this is one of the possible views that we can have. So we can show all the 4 power stations, and we can have the movement of the robot while it is happening. So we can use MindViewer to track the position of the robot on the environment, and we can see when it's reaching a target and when it's going away from one of these power stations. Okay. We can also try to monitor the different actions that are being taken by the robot in each time. So we can see that also in a moving window. So we can see these things happening in real time. We can monitor, for example, the robot energy being visualized by the MindViewer, or we can see the curiosity heat map that is provided by the MindViewer. So we can see that at this particular point, there is a great curiosity in this particular point where is the power station is located, okay? Well, there are other visualization features that are not used in this particular example. We have, for example, the idea tree in real time that can be used on online variable inspection. We can have a geographic map that is constructed using the OpenStreetMap maps, where we can, for example, if we get information from a mobile phone, a GPS coordinates, for example, we can show that into a real map, and we can show someone moving around in the environment using our visualization tool. Okay. We have many different kinds of heat maps with multiple color scales. We have also what we call a custom viewer. This custom viewer is quite interesting in the case that we have a visualization that is too much specific for a particular situation. We can then build this visualization and make it available on the MindViewer as well. Okay. The desktop MindViewer interface can integrate virtually any custom visualization that can be constructed using the Java language. Okay, and also we have integrated visualization in Java and JSON-oriented URLs provided by the CST kernel. We have created a class in CST that made all the inner variables available as REST endpoints. And then the web application can connect to these endpoints and use this information for a visualization of what is happening inside the architecture. Okay, the web MindViewer is a standalone application that was written using Node.js and React using the JSON-oriented inspection tool. Okay. Well, as a conclusion, we have presented you the MindViewer, that we have 2 different versions, the desktop version and the web version. The desktop MindViewer is a Java class with its own JFrame, which can be created from within any application that uses CST. It runs together with the cognitive architecture, and it can be made visible or invisible depending on the user's request. And the WebMind Viewer is a standalone web application that inspects the cognitive architecture built with CST. So the internal variables are exposed using JSON and URLs. And now we are working in a new improvement for our web Mind Viewer. We are trying to create a set of standards and protocols for the exposure of the cognitive architecture's internal variables, such that the Mind Viewer can be used not only with CST, which is actually the case, but we expect it to be virtually, it can be used virtually with any cognitive architecture that follows these standards and protocols. So we can, for example, if you are developing your own cognitive architectures, and you can use these standards and protocols, and then you can use the Mind Viewer for viewing whatever is happening inside your cognitive architecture, for example. Okay, well, that's it. Thank you. If there are any questions, I'll be very happy to answer.
We'll now proceed with the next presentation.
No question.
Sorry. Now we will proceed with the question from the audience. If anyone has any question. What kind of errors are you expecting to find with the debugger?
What?
Errors. What kind of errors are you expecting to find?
Oh, it will be behavior errors. So you are expecting the system to act in one way, and then you just realize that it's not doing exactly what you would expect to find. Or, for example, if you have a complex inside mechanism, for example, for episodic memory, and you have an idea that it should be working like some way, then the final behavior is not compatible to what you are expecting. Then you can get to the details of each part of your model, and then you can trace what is going wrong and in which part, in each component of the architecture, the problem might be appearing.
How do the debugger knows that it's an error?
Well, the debugger by itself is not going to know, but you know because you have made the model, and so you know how the model is expected to work. And then you can say, oh, this variable should be changing, and it's not changing, it's fixed. Then you can trace that there is an error.
So it's like interaction.
Yes, it's just like you seeing what is happening inside your architecture in real time while it's operating. Okay. Welcome.
This afternoon we saw Macintosh presentation. So he's trying to create or use, or rather he used image to construct a brain, a virtual brain. So do you think it is possible to present by means of image this debugger, or just image as
yes. Yes, we actually don't have, for example, an image of the brain that you could show which part of the brain is triggering, but this is easily constructible with our custom viewers.
Yeah.
So it's just a matter of having constructed a visualization entity in Java, for example, and then we can plug this visualization together in the Mind Viewer and use it inside Mind Viewer. So it's a kind of extensibility thing that the Mind Viewer provides. And well, it has this little effort for constructing that, but once you construct that, it can be integrated into the Mind Viewer and it can be used in further situations, in further uses.
Okay, and this is my first question, but the second one is very linked to the first one, because we don't know exactly what is a good behavior. Yeah.
So it depends on the inputs.
Yeah.
Yeah. So in my point of view, the problem can come from many things.
Yes.
For instance, if you connect, make the wrong connection, you can have a wrong result. So there is something like standards, bilateralish, for instance, that present the way rather connections between different brain areas. Do you consider that this debugger can take into account that way to verify if the connection are wrong or right?
Let me say what we can do. Today, without the debugger, you can only see the inputs and the outputs. You cannot see what is happening inside the architecture. What the debugger can give you is a way of seeing what is happening inside the architecture in some specific way. Okay, but the exact kind of error that we are wanting to trigger will require some knowledge of the model. So you will, of course, that you need to understand your model, but you can find, for example, that a model that you implemented to do such a thing is not doing what you expected it to do. And then you can find that with this viewer. Okay. It will require some extra effort maybe for doing exactly this, what you're proposing. But as I said, it's just a matter of figuring out a custom viewer for this, and then I believe that it is possible to show you if you are able to construct this custom view.
Yeah.
Okay.
Okay. Thank you.
Thank you. Okay. Thank you for all the questions.
Thank you. We will now proceed with the next presentation. We shall start Gustavo's presentation.
No uso Max, Doc. ¿Por qué me hace estas cosas? Nah, quiero pensar que sí.
Sí.
Debería aparecer por aquí. Sí, es
No sé cuál es.
según yo es este, ¿no?
Entonces, pica.
Pero, es este, de hecho. Pero no me lo quiero ver. ¿Sí es PowerPoint?
Sí.
No lo quiero ver.
Está.
Bueno, dejar de comparar. De todas maneras. ¿Cómo abro una ventana de acá atrás, no?
Ok, mejor en este.
Finder, no. Y este acá. Sí. No sé por qué no lo quiso abrir.
Te compartes. Lo abres y te compartes. ¿Ya?
Nada más que lo abro.
Sí. Está muy pesado para entender.
Es que Carlos dejó como 20,000 diapositivas. environments. So, well, these are this is the schedule. Some of the things we're going to go through. So first, I work, or well, the team works in the development of a cognitive architecture named Guadalajara, whose main goal is to produce human-like behavior, taking neuroscience, psychology, and computer science as the theoretical basis. In order to achieve this goal, we've divided the architecture in several cognitive functions, which can work together or ideally together or in isolation. Some of those are shown in this diagram on the right. Now, the pervasive system, composition systems, the pervasive systems are systems which are in constant change. So to deal with this kind of environments, we need a highly resilient and flexible system to deal with them. One approach to those is the service composition systems, which some of the students with Dr. Felix are working on. Most of those systems follow the same set of steps, which are shown in the slide. And some talk has been made about the possibility of using a cognitive architecture as this composition system. Why? Well, because cognitive architectures would ideally be very flexible and resilient. So, well, naturally, with this assumption, some questions arise. Questions such as, is the cognitive architecture enough to solve any specific problem? Are all the cognitive functions necessary to solve any specific problem? Given a specific problem, what are the essential necessary cognitive functions needed to solve it? Does the way that information is presented to the architecture affect its performance? And what is the way, well, if so, which is the best way to present that information to the architecture? So, well, also we know that the architecture is going to have sensors and a perceptual system. So the way the information is perceived by the architecture could affect the results. So does that way of getting the information affect the performance? And which is the best way to show that that information? So we have these questions, and one way to answer them, since we do not have a complete cognitive architecture implemented, we thought about doing some tests to answer those questions using what would be a complete cognitive architecture, which is human beings. So we designed some tests with the objective of determining first the feasibility of using what is called dissimilarity matrices to evaluate human behavior and thus a cognitive architecture in its due time. We tried to determine the best way to present the information to the cognitive architecture, and we wanted to find the critical factors or which attributes would the architecture need to solve a specific task. So for that, we divided this experiment into two parts. The first one were a series of psychological tests in which we obtained from humans their intelligence level, their visual detection capacity, digit detection, their successive series, that is a memory test, if I recall correctly, and progressive digits. While doing these tests, we took the results of each human and generated a vector, which we would use later to compare the results among humans. The second part of the experiment consisted in creating a virtual environment on which the humans would be asked to perform a certain task. On this case, it was to move a drone on the map seen on the left and find the goal, which is the red square on the right. For that, the humans were given a virtual reality headset, and they had to manipulate the drone with a controller. The catch is that humans would not be seeing the map on first person as we normally do. The map would have fixed cameras along the way, and they would have to use those cameras as if they were CCTV cameras, switching between them and using those different perspectives to find the goal. While they were doing that, we would measure performance, that is their ability to finish the task, find the goal, the remaining battery on the drone, which could be translated as time remaining, and how many times the drone crashed with the environment. Those are the things that we consider would be important on a similar task, but done by a cognitive architecture to take into account. So we took those results and generated another vector with them. We got several of these vectors for each human, 10 vectors for each human, and the psychology tests as well. So taking all the information that we placed in these vectors, we generated a larger vector for each human, which we then used to compare the results from each human, the results from each human compared to themselves first, and then each human compared to the other humans. Now, this is called the similarity matrix. Similarity matrix. And what it measures is how similar the results are from each human compared to every other human. Ideally, if humans had similar results, we would expect to see a lot of yellow on this graph, which we do not. So that means that humans did not show consistent results between them. We, however, found that even though most humans did not show similar results between them, they shared some other common aspects. Mainly, it seemed, although it's a very small margin, but it seemed that by showing the information one camera at a time, that would result in a slightly better performance than the other way, which was show all the available cameras at the same time. We think that that small improvement is due to the fact that one camera at a time drains the attention slower than, say, 5 cameras at the same time. So later, what we did was we tried to find which of the capabilities resulting from the psychological tests were determined how likely it was for them to succeed in the task. We took the best results from each of the 2 groups we took of humans. The first one was elementary school children. And we took the results with correlation higher than 60%, which are shown with a little arrow. And we tried to calculate the p-value just to see if the correlation was true. Our results show that they are. and that there is a correlation between performance and, say, intelligence and digit detection, which would be the lowermost left square on that graph, right? What seemed curious at the time is that for most of the results, children which had a high say mark on all the tests usually did not perform well on the test, which would sound counterproductive, well, counterintuitive at first sight, right? We then did the same thing with PhD students, and we found all the values with correlation higher than 50%. And we also found some correlation between some of the tests and a high performance value. Something that, well, jumps or is very noticeable at first sight is that for children and adults, it's not the same kind of psychological tests which need to be high for them to have a high performance. So that means that a more developed brain would need some different kind of intelligence to perform well on these kind of tests. So in the end, what conclusions can we draw from this experiment? Or how did we fare with our initial objectives? First, given the proposed experiment, which is the maze-like virtual environment, determine the feasibility of using dissimilarity matrices to evaluate human behavior. We found that we cannot do that, at least for such complex experiment, because humans are not that similar in the results, and noise can be confused with a human. So since we cannot compare humans between themselves using these matrices, we cannot compare a cognitive architecture either. Determine a better way to present information. Well, we found that at least in this experiment, showing one camera at a time results in a better performance, although small. So we think we should do more tests only to find a better result. And find the critical factors involved in solving the task. We did manage to find them, and we shown the correlation value. So that's something good. Now, what's left for us? What are we working on, and what's on the future? First, we know that the correlation between the performance and the psychological tests differ in which areas truly affect the performance for both groups, which I've shown. The results indicate that on average, only one input at a time is desirable to obtain a better performance instead of several inputs at the same time. When given the option to use the drone camera, and that is a first-person view of the drone, the participants on the experiment would prefer using that camera instead of the CCTV's cameras that would show the drone in a third-person perspective. We believe that this is related to how we perceive the world. We perceive everything from our eyes, which means that is a first-person view. So most of our skills are tuned to work that way. We now are working on looking and finding a set of psychological tests that could be directly correlated with the cognitive functions in which we divide the architecture. Another point under development is the abstraction of some mechanisms that could simulate the myelination at different levels in different cognitive functions. That is the difference between a developed and underdeveloped brain. Those mechanisms would allow us to explore whether these levels of myelinations are responsible for making the brain operate differently at different ages. We are also developing a methodology that would allow us to streamline the configuration of a cognitive architecture. That is, we would be better equipped to select both the functions related to a certain task and how those functions must be tuned in to obtain the best performance in this kind of systems. And well, that would be taken, since our cognitive architecture looks to work as a human, we would test on humans first to get those values. So that would be all. Thank you for listening, and if you have any questions, go on.
Now we will proceed the questions.
Can you explain better the triangles in slide 21, I believe? Yeah, I could not understand the meaning of these triangles. If you can give us a better understanding of what you're showing with them.
Sure. Let me just. Okay, let me just come over here. Okay, so what we are showing, I think it's hard to see over here, but
for example, this line performance.
We have performance.
What is the meaning of each of these boxes there?
Performance is how good the humans were at solving the test. And we have several columns, A, B, C, D, E, and that's where the correlation comes from.
But what about the two first boxes there, the white and the red one?
We're not taking values from them because what we are checking is just performance, battery, and crashes.
Okay.
So these values, we're not comparing battery against performance, but we are comparing performance against A, and A means intelligence test.
Okay.
So this square over here would be the correlation between the performance and the intelligence of the participant.
So this just for the A, B, C, D, E, not for the three first ones?
Yes, the first three should not be counted.
You made that just to make it triangular, but maybe you could just put the three first connected and with a cut triangle, it should be more understandable.
Well, yes, maybe it would.
Okay, now I understood. Yeah, okay. I was not understanding the whole meaning of the triangle because there are some of the points that are not making sense to me. So that's my problem with it.
Yeah, and the other triangles show the correlation between having high stats, but with all the combination of tests.
Okay, thank you.
Questions?
No. ¿Estás viendo tu film?
Okay, thank you.
Okay, thank you very much.
We will proceed with the next presentation. We shall start with Kazutero Miyazaki's presentation.
Yes, I'm here.
Thank you, Kazutero. Are you ready to start your presentation?
Yes.
Go ahead.
I am Kazutero Miyazaki from Japan. Today, I'd like to present modeling of placebo effects in stochastic reward tasks by reinforcement learning. This is outline of my main points. Several studies in the computational psychiatry field focus on modeling diseases using reinforcement learning. This study aimed to model through reinforcement learning using real data of stochastic reward with regard to the placebo effect. We modeled the placebo effect using real data related to the non-invasive brain stimulation technique, NIBS, such as TDCS and TNIRS. The result of our method shows no difference with human data. This study uses the 29 healthy male data in this paper. First, the participants engaged in the baseline session, in which no intervention was made. The baseline session was followed by 2 balanced and active placebo sessions that were randomly ordered. They are expressed as A and B, corresponding to low and high uncertainty. The participants were assigned stochastic reward tasks with 3 levels of difficulty: 80-20%, 70-30%, 60 or 40% for each symbol pair, where 3 pairs of Chinese symbols, different ones for each session. The images in the first line, A to F, are shown in the practice session. The second line, Z to I, are in the baseline session. The third line, M to R, are in the low uncertainty. The fourth line, S to X, are in high uncertainty. The value in percent indicates the probability of receiving a reward. The probability getting a reward is constant in the experiment. The participants were asked to choose the stimulus with the highest reward probability from the symbol pairs. The tasks were composed of 6 blocks with 60 stimuli in each block. In A, low uncertainty, the participants were told they would receive a composed stimulation TDCS and TNIRS, a standard and effective intervention for improving cognition. In B, high uncertainty, the participants were told they would receive a TDCS intervention whose effectiveness had not yet been improved. Through the participant and data collector were uninformed, TNIRS were inactive. Therefore, the skin sensation induced by the stimulation was psychological equivalent in the 2 placebo sessions. When a participant chooses an image with a high probability of getting a reward, it is considered as a correct answer. For each participant, we calculate the average correct answer rate across all the 180 pairs of stimuli. The average values show that A or B have a higher correct answer rate than N. N is baseline session, which confirm the presence of the placebo effect. Focusing on the correct answer rate for each participant, it is possible to observe a variation in the difference in the correct answer rate in N, A, and B of each participant. Therefore, we not only model as an average value, but also the variation in the difference of each participant. We performed reinforcement learning executed with the symbol pair presented as a sensory input and the participant's choice as an action. Reinforcement learning method uses were Q-learning and proxy-sharing, where the evaluation value to be learned is denoted as the Q value. We initialize the Q value with the following 4 patterns: P00, P01, P10, and P11, where 1 means the part each part is correspond to participant and placebo. The part that initialize according to change in the effect of the participant or placebo. For example, P01 means the Q value is not initialized when the participant changes. However, it is initialized when the effect of the change. This is a result of our experiment. There is not much difference between A and B with any pattern. Therefore, we only use the result of P00 later. Though the algorithm runs by reward, the probability of the reward is always constant. Therefore, the participant may generate different results with N, A, and B, depending on the atmosphere at the moment. However, reinforcement learning runs without being influenced by such factors. The data of human participants show a unique pattern for each participant. Therefore, next, we model it using proficiency. The kind of modeling was achieved by adjusting the Q-learning values, temperature parameters such of Boltzmann selections. However, regarding the data using in this study, when the action was selected by Boltzmann selection, the correct answer rate dropped sharply. Therefore, we decide to fit the model with other than Boltzmann selection. We set the parameter Ikichi that works as threshold for action selection. This indicated that an action is only considered if it exceeds Ikichi. It is possible to produce various behaviors by changing Ikichi. Ikichi assumed 0 and 1, 10, 100 and compared them. It is also possible that some participants have better memories than the others. We had the idea of introducing the Kyoku 0.0 from 1.0, a parameter that determines the probability of blocking a choice with a certain probability before the final output. If Ikichi equals 1.0, the action is output as per the participant choice. Nevertheless, as the value becomes closer to 0.0, the probability that the action output is in accordance with the choice decreases. In addition, a certain known as sum, which is used to calculate the difference in the Q value between two choices. If the value when the Q value of choice B is subtracted from the Q value of choice A is larger than 7, the action prompted by the Q value of choice A is considered. 7 assumes 0 and 10, 100 and compared them. Lastly, it is possible to set coffee as another parameter as sharing. Since the value equal to or smaller than coffee equals 0.5 satisfy the rationality theorem of profit sharing. We attempt to fit the model by changing coffees with this range. Therefore, model fitting is attempted by changing the 4 parameters such that Ikichi, Kyoku, Sabun, and coffee. The model result by profit sharing related to the result previously. Table 2 P00 and best match indicate the model error, which is calculated as the square root of the sum of squares of the difference between the correct answer rate for each the 180 pairs of data and the obtained as the result of the modeling. The smaller values, the better. Though table 2 P00 is the modeling error when modeling with P00, the value of N, A, and B are the correct answer rate when modeling with the parameter values shown in such Ikichi, Kyoku, Sabun, Kohia. And the value of best match is the modeling error when the value of NAB are used. This result confirms that the modeling error of the best match, is reduced compared to the table 2 P00. It is presumed that the participants who have a higher correct answer rate because of the placebo effect are able to demonstrate their full potential. This is because something that is normally guarded by Ikichi is released. The case of the participant whose correct answer rate is lower because of the placebo effect, it is presumed that they become overly conscious with the equipment installed. These are the conscious guard that suppresses their true potential. In this study, the conscious guard is well controlled by Ikichi. Moreover, it is confirmed that people with bad memory can be modeled with a kyoku value than 1.0 as the baseline. Conclusion. We modeled stochastic reward tasks using reinforcement learning. In contrast to human data, the result of the reinforcement learning approach shows no difference owing to the differences in the placebo effect. By appropriately adjusting the modeling parameter of profit sharing, we were able to model each individual difference pattern appropriately. In the future, we intend to use deep reinforcement learning to achieve modeling with higher goodness of fit. Thank you for your attention.
We will proceed with the questions. If anyone in the audience has further questions, please raise your hand. Okay, this concludes the presentation of this blog and the day. That's thanks to all presenters and to all the members of the audience. Activities will continue tomorrow and the specific time. Thank you.
Thank you.